schedule. So it's there will be 4 talks, right? And normally it should end as yesterday at 6:30.
So at 6:30, I'll come back.
Okay, perfect. Or if there is anything happening in the meantime, I'll write to you. But normally I would expect it should be fine.
Okay, so YouTube is running.
Could you send me again the YouTube reference? Actually, I don't know. Yesterday, nobody was there. Just to say, I think it was only me. So from that,
but I see that after later several people watched it.
No, but of course we do need it anyways.
Okay, so I sent it to you both through chat and to your email.
Yeah, I have it on now. Looks good.
Okay, so then in that case, I think I'll make you the host now.
Yes, that's right. Good. Thanks.
Okay, perfect.
Perfect. Okay.
So then I think, yeah. So yeah, if anything comes up, just send me a message or email.
Okay, I think we're all set. Oh, maybe the last thing. How do you disable those sounds when people join?
Yeah, sorry, I should have. So if you click on participants, and then you
yes,
and then you click on the more,
right? Okay,
and there should be play, exit, entrance, chime, or something like that, and you should just untick it.
Okay, let me just answer the phone. Алло. Володь, привет. Слушай, я не очень могу, я тут на какое-то должен начинать мероприятие. Можно я тебе перезвоню, как освобожусь? Куда вы поехали? Ну слушай, молодцы, ладно, я попробую позвонить. Okay, yeah, sorry. So
I did it. I reclaimed host and I changed the settings, so there should be no more chiming. But normally it's under this button more, and it says play, enter / exit chime, and you just need to tick it or untick it.
Okay. Yeah, you can now transfer it back, and I think we're all set.
Okay, sounds good.
Thank you.
Okay. See you later.
See you later. Clément?
Yes.
Hello. So would you like already to try to share the screen for you to show your file?
Yeah. Is it okay?
Yeah. Wait, let me see. I think. Yeah, it looks good to me, right? I do see your screen very clearly. Okay, looks perfect. So I think most probably we'll have to wait 1 or 2 minutes after 2 o'clock just to let more people in?
Yeah, sounds good.
Mhm. And then after the talks, I suggest that you take the discussion session 3
Okay.
for answering questions and talking to the audience.
Okay.
Of course, I will repeat it many times, but since now we have some minutes, it's probably good to agree on that.
Sure.
Mhm. So where is this Max Planck for quantum optics?
Munich. It's in Munich. Well, it's next to Munich in Garching.
In Garching? Oh, but there are many Max Planck institutes, is it right?
There are 6, I think.
Wow.
Yes.
Oh, that's a lot.
The only one in Munich is the physics one.
Mm-hmm.
That was the first one, actually.
Mm-hmm. Yeah, I recall. I think I probably even once visited Garching. So it's not that far from Munich, right?
No, there was a subway. It's like 15 minutes
Mm-hmm.
with a subway.
Yeah, so our program seems to be really intense. So let's hope people will be able to attend till the end of the week, right? But kind of.
Yeah, but it's nice.
Yeah, no, absolutely. Yeah, I think all the talks are very nice. It just kind of not so easy to pass that much time on Zoom.
Yeah, I agree.
Mm-hmm. Yeah, but I guess Chen Chang, she's marrying on herself, so she's workaholic. So that's how the program looks like.
Makes sense.
Yeah, that's right. So how is it in Germany now? Are there many restrictions because of COVID, or is it
Not really, no. I mean, since the beginning, I think the confinement wasn't as strict as in other European countries because they managed to maintain a bit like a lower level of.
But do you need to wear masks somewhere or nowhere, or what's?
Well, at the institute we do, but I'm not sure what's I think in stores and in restaurants we have to.
Mm-hmm.
Yeah.
So it sounds like all public places, is it right?
Well, I'm not sure actually. I forgot, but I think it's mainly restaurants and stores. That's for sure.
But if you forgot, this means it's not so strict.
Well, yeah, I guess. I don't know.
Right?
Oh, I just never go out, so that's why.
Yeah, if it was strict, it's difficult to forget, right? I mean, yeah.
Well, we cannot share offices, so.
Mm-hmm. Oh, I see.
Everybody needs at least 10 square meters of space. So if we have less, we cannot share offices.
Mm-hmm. Right, we just returned from vacations on Mallorca, and there, in principle, in theory, you should also wear masks in the street. And sometimes if you don't, then people tell you, like, why don't you?
Well, it's good, I guess.
Well, I don't know whether it's good, but in this, I think in the streets, I'm not sure to what extent it makes sense, but maybe it does. Difficult to say.
Yeah, I know in some cities they are doing it right now in some countries.
Yeah, it probably depends on the density. If you really have a high density, people close to each other, then yes. But if you're walking the beach, well, probably doesn't make that much sense. Okay, so I think we can slowly start. Welcome to this Wednesday session of our workshop. And the first speaker is Clément Declan. And the title is Excitations in Strict Two Groups, Higher Gauge Models of Topological Phases.
Thank you. First of all, I'd like to thank the organizers for putting together this nice workshop and for giving me the opportunity to speak. And so today, I want to discuss some techniques which are quite useful in order to study excitations in models of topological phases. And I will illustrate these techniques with a special class of models that have a higher gauge theory interpretation, whose input data is like a categorification of the notion of group, namely a strict group. And this is work with in collaboration with Alex Bolivant, who's the next speaker, actually. So during this talk, by a topological phase of matter, I will mean the following. An equivalence class of gapped local quantum models that have a common low energy description in terms of a topological quantum field theory, TQFT. And my focus will not be on these TQFTs per se, but really the quantum models that are concrete realization of a given phase. And more specifically, I will consider models that you can build in a rather canonical way from a state-sum TQFT. In that case, I will refer to them as the lattice Hamiltonian realization of the underlying TQFT. So for instance, in 2+1 dimension, models of non-chiral topological phases can be constructed from the so-called Thierry-Viro state-sum TQFT in its fully extended form. The input data being a so-called spherical fusion category, and this construction, the lattice Hamiltonian realization in that case is referred to as a stringlet model, and it's due to a Levinian one. So let me sketch a bit loosely the the relation between the lattice Hamiltonian and the underlying state-sum TQFT. So let's say I have a D+1 dimensional state-sum TQFT, a topological lattice model consists of an oriented D-manifold surface, which I equip with a discretization, usually with a bit of additional structure. So for instance, triangulation, or I will later consider cubulation. Then we need a set of classical configuration variables, which we assign to the cells of our discretization. And the microscopic Hilbert space of the theory is then given as the sort of formal linear superposition of these colored cells. The Hamiltonian operator generically is obtained as a sum of local operators, which act on local neighborhoods of the cells of my discretization. And these local operators can be neatly defined in terms of what the state-sum TQFT assigns to a special family of cobordisms. And then this is kind of the key point, because then we can use the topological invariance of the theory to infer a lot of properties. So for instance, the topological invariance will imply that the operators are projectors and they are mutually commuting, such that the model is exactly solvable. And the ground state subspace of the Hamiltonian, which is by definition the space of states that satisfy the stabilizer constraints. So this H phi equals phi condition. So for every operator, there is one such stabilizer constraint, and the states satisfying all of these are ground states. And then this ground state subspace turns out to correspond to the vector space that the TQFT assigns to this space.
Furthermore, I have a very naive question. So you, of course, I don't know at all what's going on, but how is it you want this phi in the definition of the ground state to be an eigenvector of H with eigenvalue 1, and not 0, right? Usually, because oftentimes.
Yeah, I mean, you can rescale your Hamiltonian such that it would be 0, but written as it is, in that case, the ground state will be
Yeah, I just usually, right, if you normalize the ground state energy,
sure.
want to say that it's 0. But
you can write 1 minus the operators instead of the way I written it. In that case, it's, yeah. And furthermore, it follows from the topological invariance that if I pick a different triangulation or different discretization, the ground state subspaces are isomorphic. And this will turn out to be quite useful in practice when we do computations. So I already mentioned in 2+1D the string net models, right? So the dictionary in that case, more specifically between the TQFT and the Hamiltonian picture, is the following. We have that the ground state degeneracy, which is the number of independent states in my ground state subspace, is equal to the number that the TQFT assigns to the manifold sigma across S1. Similarly, as already mentioned, the ground state subspace is what the TQFT assigns to the corresponding space. And excitations, finally, which is really the feature I will be focusing on. Excitations, which are by definition microscopic states that violate some stabilizer conditions, right? So they don't fulfill all of them. And these are found to form, or they correspond to the objects in a rather famous category theoretical structure referred to as the Grunfeld center of the input category. This will not be crucial for my talk, so don't worry if you don't know these notions. And these
sorry, Clement, one more technical question. So people are asking whether you can share with us your slides. If it's complicated, then forget it. Or if it's easy, you can simply paste the PDF file in the chat. And then people can, whatever, maybe they want to return and check some things that you were talking about some minutes ago. That's usually very convenient.
Yeah.
Thanks a lot.
Okay.
Now there it is. Thank you.
Okay, and so the reason why these excitations are interesting, right, in these models, is because in 2+1D they correspond to quasi-particles with an Anyonic statistics. So mathematically, this is a statement that these provide representation of the braid group. Physically, this is a statement that these particles have statistics that is beyond the bosonic and the fermionic one. And in order to appreciate the fact that we can have anyons in 2+1D, there is this famous cartoon, which is that if you have two particles, right, you can exchange them following a specific trajectory. And then the double exchange of these particles, so it's like going back to the original position, is equivalent to fixing one and going around with the other one. And then the loop described by this particle in 2+1D can be topologically non-trivial in the sense that it cannot be contracted to a point because there is the other particle obstructing. And therefore, the corresponding process is not necessarily the identity, which means that these phase factors exponential I-phi are not necessarily plus or minus 1, which would give us bosons or fermions. And the same picture also allows us to understand why we cannot have anyons in 3+1D. Because if you have an extra dimension, you can use this dimension to contract this loop to a point, and therefore the process has to be trivial. But using similar arguments, we can intuit that if we had higher dimensional particles, so let's say string-like or loop-like particles, then these could actually have maybe an Anyonic statistics. So let me focus now on a special class of models, which is like, so it's a special case.
If it's higher dimensional, what will happen? I just missed that.
Well, the point is to say that, okay, we know that point-like particles will have to be bosons or fermions. But if we have higher dimensional particles, well, quasi-particles, so let's say like it would be like a string-like excitation, a loop-like excitation, these could, in principle, have statistics that is beyond the bosonic and fermionic one. So in order to compensate for the fact that we are in higher dimension, we need to have higher dimensional excitations.
Thanks.
Does it make sense?
Maybe later. Thanks.
I will describe later what is the statistics of this loop-like excitation and explain in which way they are onions. So, so a special case of or a special class of stringlet models are given by picking the input category to be this category of G-graded vector spaces. And what matters right now is that this has two, the input data of this category is a finite group, G, and a cohomology class in the third cohomology of the group that characterize the monoidal associator of the category. And these models, they are nice because they have a gauge theory interpretation. So how are they constructed, roughly? The microscopic Hilbert space is given as the formal linear superpositions of group colored triangulations, where by that I mean we put a group variable on every edge of the triangulation, and this defines the notion of G of group connection. So it's like the space of group connection. Sure. Then the Hamiltonian operator is given as a sum of two families of operators, so A and B, that are labeled by vertices and plaquettes of my triangulation. And these encode the two kinds of constraints. So the first one is a gauge invariance, because I said it had a gauge theory interpretation. It's a gauge invariance that is sort of twisted by a phase factor that depends on the input 3 cycle. And there is another constraint, which is a flatness constraint, which essentially penalizes a non-flat G connection. So, okay, and now, since it's a special case of what I mentioned before, we know that the excitations, they will be characterized by this center of the input category. But what's really nice about this model is that there is an equivalent description of this category in terms of modules or representations of the so-called quantum double of the group, which is an algebra. And the reason this is nice is because this algebra shows up quite naturally in the Hamiltonian picture in different ways, but in particular as the so-called algebra of excited states. And I will explain now what I mean by that. So in order to reveal, what we want to do now is essentially to reveal this algebraic structure, because then we know that just taking the representations over it will give us...
I'm sorry, I missed again. So the point like is in the bulk, or
Yeah, the excitations are. I just wanted to emphasize that these are bulk excitations. So there is no boundary at this point. There is no gap boundary. It's really a bulk excitation.
Okay.
So in order to reveal this algebraic structure, we're going to use the so-called tube algebra approach. So in general, if I think of an excitation as a region of my manifold for which the energy is higher than the one of the ground state, the tube algebra approach relies on the following idea, which can be motivated in different ways physically, namely that the properties of an excitation are encoded into the boundary conditions of the manifold obtained by removing this region. So let me make this more precise. Let's say we have a point-like excitation. There will be a region around this point-like excitation, a disk-like region for which the energy will be higher than the one of the ground state. Now, if I remove this region, I'm left with a circle boundary, right? Boundary that has a topology of a circle. And my Hamiltonian or my ground state projector does not act on this boundary that I just created, which means I have now boundary conditions. And the idea is that classifying these boundary conditions is the same as classifying the point-like particles. So I have some drawings below. So the red region is my region with a higher energy, right, which I removed, and I have this circle boundary. And now, purely the topological level, I can do the following, which is to glue a cylinder on top of my circle. And then I can use an orientation preserving diffeomorphism in order to absorb this cylinder on my surface, so that I'm back with the original surface. So in other words, it's like gluing a cylinder on top of my boundary does not change the topology. Now this induces a map at the level of the ground states. So now the idea is that, so this, I want to translate algebraically this topological statement. And to do so, I'm going to lift it at the level of states, ground states on the corresponding manifolds. So what I mean by this is that this induces kind of a symmetrical operation where I'm acting with ground states on the cylinder with ground states on my open manifold, and I will be the result will be again a ground states on my open manifold. So let me make this a bit more precise. So similarly, right, we can do the similar topological operation. We can take two cylinders, glue them, right? So we're just left with a bigger cylinder. And then with the diffeomorphism, we can just sort of reduce its length so that it looks like the original ones. Now, again, at the level of the ground state subspaces, right? This induces, in that case, an algebra structure, because I'm starting from two states from the two copies of the ground state subspace of the cylinder, and the result will be a state in the original ground state subspace. So how is it defined, this algebraic structure?
Clément, just an information. Why are you saying that this algebra is semi-simple?
Well, you can show it semi-simple. I mean, from what I'm explaining right now, it's not, of course, obvious, but you can, once you have it, you can check that this is associative, semi-simple, and you also have a star algebraic structure.
Okay.
So how is it defined, right? So you take two states, right, in the two copies of the ground state subspace. Then, so the gluing operation, algebraically, how it translates, well, it's an identification of the boundary conditions. So we have boundary conditions on these circles, right? And the circles along which we do the gluing, where we have to make sure that the boundary conditions match. So in practice, it means that we're going to multiply by some Kronecker delta that enforces this matching. Now, the subtlety is that the resulting states are not necessarily ground states anymore. Which means we need to act with the ground state projector in order to recover our ground states. And once we have this, we can do a unitary transformation, which is the algebraic translation of the diffeomorphism. And at which point we have a state that is in the original vector spaces, and that's how we have an algebra. And this is what is referred to as the tube algebra. And the notation here is, so it's the tube algebra associated with the circle.
Can I ask a question?
Uh-huh.
So why is it, when it's glued together, why do you say that it is not the ground state anymore, or it might not be the ground state?
So the ground state projector does not act at the boundary, right? So if I look at the cylinder, right, on the edges, right, or on the boundary, the ground state projector does not act. Then this operation here is just identifying the boundary conditions. So there is no reason why, for instance, the gauge invariance is, in the case of gauge models, should be enforced at the meeting vertex, the vertex at which they meet. Because this is a vertex that was previously on the boundary, now it's in the bulk, but there is no reason why the gauge invariance should be enforced there. So we have like a new bulk vertex, and we have to ensure that the gauge invariance is satisfied at this bulk vertex.
All right, I have another question. So the cylinder you drawed, each one does not have the structure of cylinder alone. It also has some boundary conditions on it, right?
Yeah, so here, okay, it's a bit of a symbolic notation, right? What I mean by my notation here is that the V, right, is the ground state subspace for the cylinder. So then in practice, I will have to actually write down such state. I will pick a triangulation, put labelings on the edges, and this will define like explicit states.
But most importantly, it also may have some different boundary conditions on it, right?
Exactly, yes. So, I mean, here boundary conditions, what it means that if you want the group variable or the holonomy along the circles along which the gluing is performed is not necessarily the same. So we have to make sure this is the same when we do the gluing.
Okay, I get it. Thank you.
Okay, so putting everything, putting everything together we have so far, this induces that the ground state subspace on the open manifold has a module structure over the tube algebra. And what we need are essentially to find the simple modules, and this will classify the boundary conditions on my circle boundary. Now, again, to do this, in practice, this is not exactly what we do. We use the following trick, which is that, so starting from my original surface, before gluing the cylinder, I could use a diffeomorphism in order to make my the region around the circle look like a cylinder itself. And at the level of the ground state subspaces, it just means doing a local unitary transformation. Then when I glue my cylinder, the effect of this is that it allows me to localize the action of the cylinder states on degrees of freedom that are contained within this cylinder shape itself. And then I do the same diffeomorphism to go back to the original. And then the consequence of this is that the boundary conditions, they are actually classified by the simple modules over the so-called regular module of the tube, which means essentially treating the tube itself as a tube module. And at the end of the day, the computation we're going to do is to find the irreducible representations of this tube, and this will classify the point-like excitation. Now, as I mentioned before, briefly before, to answer the question, in order to make this explicit, right, we're going to have to pick a triangulation of the different manifolds, define the group connections on it. I mean, define explicitly these ground state subspaces. And then you can ask, okay, but if I choose different triangulations, maybe it will change the tube algebra, maybe it will change what I'm classifying with. And what saves us is that for the cylinder, if we pick a different Burke triangulation, we can show that it will yield an isomorphic algebra, and therefore it's fine. And if we pick a different boundary triangulation, then it's a bit more subtle, but we can show that the tube algebras are in that case Morita equivalent. And we know that Morita equivalent algebras have the same simple modules. And therefore, we know that whichever triangulation we choose, we will always classify the same simple modules. Okay, so once we have a tube algebra, in general, these tube algebras, the irreducible representations, they can be labeled by two elements. An orbit, which is, it's an equivalence class of boundary coloring that are related by the action of my tube, and a representation which decomposes the action of the tube that leaves the boundary coloring invariant. So let me make this right away more explicit in the case of 2+1D gauge models. In that case, the ground state subspaces on the cylinder, it's quite easy because it's the same as picking a flat G connection. And to define a flat G connection on the cylinder, we only need two group variables that correspond to the holonomies along and around the cylinder. And when you apply the tube algebra approach to this, then you find that the tube algebra is isomorphic to the quantum double, which is the algebra I mentioned earlier. The irreducible representation of this quantum double are well known. There are two components, right? So the orbit, in that case, is the conjugacy class of the group. And the representation is a representation of the stabilizer of the conjugacy class. And these correspond to the flux and charge quantum number, respectively, of my sort of general or composite point-like excitation. Now we can go even further. We can endo this algebraic structure with the notion of co-multiplication and R matrix, and this will encode the statistics of the excitation. So its braiding and its fusion. So what's particularly nice with gauge models is that they can be defined in any dimension, quite straightforwardly. So for instance, in 2+1D, well, the relevant category theoretical structure is this bi-category of G-graded two vector spaces. But what matters right now is that the input data is a finite group again, and now a 4 cocycle instead of a 3 cocycle in 2+1D. And these Hamiltonian models in 2+1D, they yield not only point-like excitation like in 2+1D, but loop-like fluxes and point-like charge excitations. And now what we want to do is essentially to classify so the most general kind of loop-like excitation, and we are going to use the tube algebra approach again. Now the difference is that now, since the excitation has the topology of a circle, right, before it has the topology of a point, the energy which will have the region for which the energy will be higher than the one of the ground state will now have the topology of a solid torus, which is like a regular neighborhood of my loop. And my elementary loop-like excitation will be classified by irreducible representations of the corresponding tube algebra, where the tube, right? So now it's not a cylinder exactly, it's more like a three-dimensional generalization of a cylinder, where I take a torus cross an interval. And below, I drew sort of the topological operation that underlies this tube algebra, which is I take two copies of this three-dimensional cylinder, I glue them, identifying the boundary conditions and so on. And then again, via some diffeomorphism, I can recover the original topology.
Excuse me, I have a question. In 2 dimensions, the boundary only have one choice, that is the circle S1. Yeah. In 3+1 dimension, the boundary have a more choice. Here you choose to be torus. You can also choose to be sphere or genus 2 Riemann surface. So what's why you choose torus, not other things?
So here, the torus is really because this is the regular neighborhood of a loop. You could indeed consider like so actually we know how to do the computation as well if you had a more general Riemann surface, and this we could imagine correspond to classifying more complicated excitation, like maybe a connected loops or something like this. But if we are only interested in the loop-like excitation, in that case the torus is what we need. The sphere would be to classify point-like excitation, because the sphere is the regular neighborhood of a point, and you can do the computation with the sphere, and then you find that you're only classifying the charges, the charge excitations. If we want the most general composite of loop-like fluxes and point-like charges, then we need the torus. And I will give more interpretation in a second about this tube algebra. Okay, so so we have the tube algebra, right? Then we sort of apply our general recipe in order to find the irreducible representation of this tube algebra. And now the question is, how do we actually interpret this irreducible representation? And the right interpretation is that these classify loop-like fluxes to which a point-like charge is attached in such a way that the quantum numbers associated to this flux and this charge are constrained by the presence of the threading flux. So we have sort of two fluxes and one charge. So the reason this is the case, if I go back to the previous slide, is because a flux, what it is, it's a violation of a stabilizer constraint with respect to the B operator, which penalizes non-flat connection. Now, a flat connection, right, we can only have a non-trivial holonomy if we have a non-contractible cycle. So if I want to sort of create a violation of my these stabilizer conditions, one way to do it is essentially to create non-constructible cycles. And this is by sort of the torus, right? The torus has two such non-contractible cycles, which is why we have two fluxes. And the charge correspond to, if you want, like a violation of the gauge invariance at the vertex at which these two contractible cycles intersect, non-contractible cycles. Now, what this implies, so the cartoon to understand what I just said is that you have these loops, right, where you think of it as a flux plus a charge, and then you have this threading flux that goes through the loop. And what we find is that as in 2+1D, we can endo this algebra with additional algebraic structure, namely a co-multiplication and an R matrix. And in that case, the processes they describe are the following. It describes a fusion of the loop-like excitations, but this fusion can only take place if they are threaded by the same flux, which is why this additional flux is fundamental. And similarly, the braiding encoded in this R matrix. In that case, the braiding means going through, so exchanging position by going through the other loop. this can only take place if they are threaded by the same flux as well. And so this is like a way to sort of mathematically encode this so-called 3-loop braiding statistics that people have been considering for a while in the community. And we can go slightly further. We can show that the exchange statistics, so the one just well, depicted here, is governed by representation of the so-called necklace group, which is a motion group isomorphic to the braid group. And I mentioned that having representation of the braid group was like the definition of being an onion. So this is why, at the end of the day, we can say that these loop-like excitations, with respect to this braiding, behave like onions. Okay, so now, so this is the gauge models picture. What if we want to go further than that, consider a bit more complicated models? But at the same time, we would like to retain a lot of the nice features of gauge models. In that case, an obvious choice is to go to higher gauge models, where basically these are obtained by replacing the input group by so a categorification of the notion of group, which is a two-group. And these models are found to have a higher gauge theory interpretation, which roughly, very roughly speaking, is the following. If a gauge theory is the theory of a one-form gauge field that encodes the parallel transport of a point-like object, a higher gauge theory is going to be a combination of both one-form and two-form gauge fields, and this can describe, encode the parallel transport of a string-like object instead of just point-like one. And generically, these Hamiltonians, they will have 4 terms. The first 2 terms, they are analogous to the gauge models because they are with respect to the one form. So we have the gauge invariance as before, which I will refer now to as the 0-form gauge invariance to distinguish it from the other one. And the flatness condition, now I will call it the fake one flatness constraint. Fake because, as I'm going to explain, it's a bit twisted by the presence of the 2 form. And similarly, we have the analogous operators for the 2-form part, which is a 1-form gauge invariance. So this is a gauge invariance whose charges are one-dimensional, and a 2-flatness constraint that now penalizes a non-flat 2 connection. So essentially, this flatness constraint tells us that if we have a contractible 2 cycle and we have a holonomy, like a 2 holonomy around this 2 cycle, it has to be trivial.
So, okay, and somehow this V means vertex and
oh yeah, sorry. So V is vertex, P is bracket, E is edge, and C is, well, here C will mean cube later, but
so
more
it's
generally,
a cube picture. It's a cube picture. So you have 2 directions like V vertex and bracket, and then on top of it, like E is edges between V and C is edges between P. You mean this as a cube picture?
Yes, yeah. C will, yeah. I use C because later it will exactly be a cube. More generally, it could be a 3 cell. So the input, so more explicitly, right? I said the input was a 2-group. So actually, we have 2 possibilities when we say 2-group. We have strict 2 groups or weak 2 groups, where strict and weak refer to this is the category theoretical formulation or terminology. So a strict 2 group is can be succinctly defined as a monoidal category such that every object is invertible and every morphism is invertible. So this definition is nice and compact, but it's not very practical. So usually we use an equivalent description in terms of cross modules. And a cross module, it consists of 4 elements, 2 groups, both of which can be non-abelian, an action of G on H via by automorphisms, and a homomorphism from H to G. And these needs to satisfy some constraints referred to as the Pfeiffer identities. Now, weak 2 group, well, so it's a monoidal category such that every object is now weakly invertible and every morphism is invertible. And again, we don't use this definition in practice. We use the fact that these are characterized up to equivalencies by 4 elements again. a finite group, gamma 1, a finite abelian group, gamma 2, so that's one of the main distinction, an action like before, and a cohomology class, so of gamma 1 valued in gamma 2. Now, today, since I want to focus on the specificity of dealing with a higher gauge model and try to remove some of the technicalities, first of all, I will not consider, I will consider a trivial topological action. So I will not pick a non-trivial cohomology class. And also, I would like, as mentioned before, I would like to work on the cubulation to make it visually nicer, let's say, which in that case, it forces me to work with a strict 2 group. If I wanted to deal with a weak 2 group because of the cohomology class, we would need to work on the triangulation, and it would make things a bit more obscure. So, so the model we get in that case, with input a strict 2 group, is the lattice Hamiltonian realization of the so-called Yeager-Homotobi 2 type TQFT. And this TQFT has 2 sort of limiting, so these models, they have 2 limiting cases. So the first one is the one we discussed before. So if I choose the second group to be trivial, then I'm reducing to a gauge model, which I already covered. And if I'm choosing the first group to be trivial, then I have a 2-form gauge model, which you can show to be equivalent to a so-called Walker-Wang model for the corresponding premodular category. Okay, so the first thing we need in order to define a strict 2 group model is to have a notion of strict 2 group colored discretizations, or cubulation in my case. And to do so, it's relevant, very useful to go through the exercise to show the mapping exactly between cross-module and strict 2 groups. And more specifically, I will not reconstruct exactly the strict 2 group from the cross-module, but it's so-called delooping, which is a so-called one-object 2 groupoid. So it's an example of 2 categories. So this one-object 2 groupoid, well, so it has a single object, and which is represented by this black dot. The morphisms are labeled by group variables. And the 2 morphisms are labeled by H variables. And these are between morphisms labeled by G and a partial of H times G. Now, the composition rules are the following. So the composition of morphisms is dictated by the multiplication in the group. Okay? There are 2 ways of composing the 2 morphisms. Vertically first. In that case, it's dictated by the multiplication in H. And also horizontally, in which case is dictated by the multiplication in the semi-direct product of G and H. And so this is how you sort of reconstruct the delooping of a strict 2 group starting from a cross module, and you can also do the other way around in order to prove the equivalence. Now this, now using this, keeping this in mind, how do we define a strict 2 group coloring? Well, we need the notion of, well, a nice way to do it is via the notion of path 2 groupoid. So path 2 groupoid is another example of 2 groupoid, where the objects correspond to points on my surface, on a surface. The morphisms are a path between these points. And the 2 morphisms are so-called 2 paths between one path. So it's like a 2 cell, if you want, bounded by 2 one paths. And now, using this, I can concisely define a coloring of a discretization, a 2 group coloring of discretization via 2 functors from the path 2 groupoid to the delooping of my strict 2 group. So more practically, okay, how does that work? So let's say I have a surface that I'm choosing to endow with a cubulation together with a notion of branching structure. So it means having a numbering of my vertices from which I can induce essentially an orientation for the edges. And in that case, a given plaquette, it's colored as follows by a strict 2 group. So we have group elements on the edges, because the 2 functor, what it does is that it's going to map the edges of the 2 groupoid to the morphisms of my 2 group, which are labeled by edges. And similarly, we find that the plaquettes are then labeled by H variables. And what's very crucial is that these 2 functors it also preserves this condition here that my two morphisms, they can only be defined between this kind of one path. And this means that in this configuration, I must have a condition between my different group variables. And this is the so-called fake one-form flatness constraint I mentioned before. So why fake one-form flatness constraint? Well, the one-form flatness constraint would be the statement that it's a statement that holonomies along contractible cycle have to be the identity. On the lattice, it means that if I take a product of group variables around a plaquette, it has to be the identity. Now, since I have a two group, there is the two form part that is also involved. And now it's not quite a flatness constraint because I have this partial edge that sort of makes it fake. And this condition is very important because this condition ensures that this two group coloring is consistent. Otherwise, you would run into some inconsistencies. So given this, now let's look at the definition of the operators. So we have, first of all, the zero form gauge invariance, which is the usual gauge invariance. So it acts by right and left translations on the group variables, labeling the edges, meeting the vertex at which we act. So here, for instance, if I act on 0, I'm going to act by, it depends on the conventions you use, but here it means I'm going to act by left action on these two variables. And we see that there is also an action on the phase variable. And this action is here to make sure that the fake flatness constraint is always satisfied. We also have a one-form gauge invariance, which now acts on edges, and it's going to affect the plaquette variables of the plaquettes meeting at this edge. So it's going to shift the edge variable by lambda, but not quite lambda. We also have now we have a dependence on the group variables, the G group variables as well. And this again is to ensure the fake flatness is satisfied. Similarly here, we also have to act on this one for the same reason.
So, sorry, is it probably it's negotiable on which edge I would like to act, right?
Yeah, exactly. Yeah.
Okay.
If you act on 0, 2, depending on the conventions, it's yeah. And the last constraint is the so-called two flatness constraint, which penalizes non-flat two connection. So this, what it means essentially, it means that, roughly speaking, the product of the edge group variables around a contractible two cycle have to be the identity. So now my cube is one such sort of, you can think of it as my contractible two cycle. So I want to enforce that the product of the edge variables around the cube is the identity. Now, this is not quite as straightforward because you have to remember that the edge variables, right, they are morphisms, right? They have a source and a target. And in order to do this multiplication, you need to make sure that source and targets match, right, to be able to compose them in the first place. Another way to put it is that these two morphisms, they have kind of a base point. They are based at one of the vertex around the plaquette on which they are defined. And to compose these two morphisms, we need to make sure they are all based at the same base point. It's like a frame of reference. They all need to be in the same frame of reference to be able so that we can compose them. And this, so this below at the bottom, and this is this composition of the two morphisms. We see that we have to act sometimes with G variables, and you can think of this action as a parallel transport. It's like I'm parallel transporting my two morphisms so that they are all at the same base point, and therefore I can actually compose them. Okay, so these are all the constraints. Now, so from this we can define the concept subspace. And as for gauge models and topological models in general, the topological invariance implies that given different cubulations, the concept subspaces will be isomorphic. What it means in practice is that we can do local unitary transformations that change the cubulation, but we remain in the same ground state sector. So practically, it means that, for instance, if I have two neighboring plaquettes and I'm considering a ground state on this, I can sort of merge the plaquettes. It's a local transformation in order to have an isomorphic state on a single plaquette, which is the merger of the two. So using all this, we can now consider the tube algebra in 2+1D as we did for the gauge model. Let me recall that the tube algebra with respect to the manifold, which is the torus crossing interval. So in order to define the ground state subspace explicitly on this manifold, I need to pick accumulation. I should pick the simplest one possible because it doesn't matter which one I choose. So I should pick the simplest one. So in that case, it's just a cube. It's a cube such that the top and bottom faces are identified, and the front and back faces are also identified. And this gives me the topology of a torus cosine interval. Now I need to pick a flat 2 connection on this, which in that case depends on 6 scope variables. The G variables are analogous to the ones for gauge models. And we have 3 others for the to form a part of the connection. And these are constrained by the fake flatness constraint on the boundary torus, because it's a plaquette at which the fake flatness must be enforced. And on the right-hand side, there is a more symbolic notation, which maybe is helpful, which also makes explicit the fact that we can think of this element as a groupoid element. Okay, so this is just sort of a superposition of flat 2 connection. This is not yet a ground state on this manifold. The reason why is because we have to enforce the one-form gauge invariance along the single bulk edge. So this is something that doesn't happen in gauge models, because in gauge models, a flat connection is enough to write a ground state on the cylinder. Now that we have gauge invariance along edges as well, since there is a bulk edge in this manifold, we need to enforce it. So we apply the definition of the ground state projector at this edge. This is the formula below, which the details don't matter. But what it means is that it's actually labeled by an equivalence class of colorings in the bulk with respect to the one-form gauge invariance.
Clément, maybe we should discuss how much time.
I'm almost done. Yeah.
Okay, sounds good.
So the tube algebra. So I'm not going to go through the details, but visually it looks like this, right? So here I'm forgetting about the group averaging as just mentioned to keep the notation simpler. But the first thing we need to do is to do the gluing, which means, as I mentioned before, it's an identification of the boundary coloring. So here it means I will have a delta function that sort of identifies the group variables on this plaquette here with along the plaquettes, at the plaquettes along which I do the gluing. Then I need to apply the ground state projector, and then I can do a diffeomorphism in order to recover a state in the original Hilbert space. So this is visually roughly how it looks. Once we have the tube algebra, then we know how to compute the irreducible representation. Essentially, because all these tube algebras, we can rephrase them as groupoid algebras. And then we can apply the groupoid representation theory, which is like an extension of group theory, and systematically find the reducible representations. And this will classify like sort of the most general kind of loop-like excitation we can have in these models. And well, there are many components involved, and the interpretation is a bit tricky. But let me very quickly mention a few things. So the irreducible representations, they are labeled by 2 elements: an orbit, which corresponds to the magnetic quantum number, and a representation, which is the electric quantum number. Now, this magnetic quantum number, it accounts for 3 types of flux excitations. 2 one fluxes, which are the same ones we had for the gauge models, or similar ones, but also a two flux, which corresponds to the fact that the torus is a non-contractible 2 cycle, which means that I can have a 2 flux on this torus. So this magnetic number, it's like a mixture of these 3 fluxes, and the interplay between them is similar to the ones we had with the threading flux, this notion of a flux threading the loop and constraining the quantum number. Similarly, the electric quantum numbers, we have 3. One that is the 0 charge, so this is the same one or similar one as the one for gauge models. But now we also have 1 charges, so 1-dimensional charges that correspond to violation of the one-form gauge invariance along the non-contractible cycles of the torus. And there is a non-trivial interplay between all this via the different constraints, but also the fact that we have to do this group averaging to define the ground states. And in order to really disentangle all these sort of components of these different excitations, it's useful to consider limiting cases. As I mentioned before, like, you know, we know what the one limiting case is the gauge model, so we know what happens there. The other limiting case is the two-form model. The interpretation is also easy here, or easy there, and then we can sort of combine all these to derive a consistent interpretation of these excitations. Okay, so let me conclude very quickly. So this was like an illustration of the tube algebra for a model that is a bit different from the, well, a bit more complicated than gauge models. It allows us to classify the excitations. As a byproduct of the construction, we can also get the ground state subspace on the discrete torus. It can be neatly defined as the central subalgebra of the tube algebra. So that's also a nice way to get the ground states on the closed manifold. There are, well, a bunch of obvious follow-ups, which I won't even mention. Something I want to mention, which I think is quite interesting, is that as a byproduct of recent results regarding classification of 3+1D models, we know that there has to be a lot of duality relations between models in 3+1D. And in particular, we know that higher gauge models, certain higher gauge models, can be mapped to regular gauge models via a duality relation. And this is usually done at the level of the partition functions in terms of more like differential forms and so on. I think it would be interesting to understand this mechanism a bit more precisely or more, I don't know, more explicitly from a category theoretical point of view. And then from this, we could induce how to implement this duality on the lattice, and also what it means at the level of these excitations, possibly using some tube algebra techniques. Thank you very much for your attention.
Well, thanks a lot. So I think we're a little bit over time, so I suggest we postpone the questions to the discussion session, and Clément will be in the discussion session number 3. So this will be after the talks, around 6:30. The discussion sessions will start, and then so keep your questions for Clément for the discussion session 3. So now we have a short break, and we resume at 3 o'clock European time. So thank you again, Clément, for a nice talk.
Hello, Alex.
Hi, nice to meet you.
So Clément is in IHS. His actually first time to see. I guess many people. It's funny. It's first time for me to see them from internet. This is very new area. Where are you now?
I'm in Leeds, in England.
Yeah. So I think like we had some last year we have some model quite general. We have these higher gauge for non-strict higher groups too. But I think what you had really nice. I just told Liang too. Like you had this way to link the high gauge to this representation theory, what Liang works on. Hi, Clément. Yeah. In the end, I need to take screen cut all the time to help me to understand. These digital talks are all the time too fast for me. Dinos are, yeah.
You only gave us 45
nice.
minutes,
What?
There was only 45-minute slots. That's although any longer would be too long.
Yeah. There are too many exciting talks, and the yesterday it was, yeah, people didn't have time to have break. That's also not nice. So one need to find a balance. Yeah. So we were thinking. I guess yeah, it was nice to see that you actually went further, right? So even though it's strict group, that you went further to build up the representation theory out of the gauge theory, right? That was nice. So end up just to build this connection over. We actually have yeah, if you want to use our model, it's ready over there. We have actually non-strict higher group model already built up, and
yeah, I mean, it's true. We know how we could do the weak to group case. It's true that, I mean, we were trying to find like the most, like something we can easily present, right? In the strict group case is somewhat simpler to present.
Yeah. I have worked on this for a long time. I think that on higher group for a long time. So what is really easy to do is using this complex. Yeah. So you use the triangle, the triangle picture, the square picture. For a strict group, it goes okay still, but once you have non-strict, then the triangle picture, it's much more convenient.
Yeah, I mean, we had to do it. I mean, for the gauge case, since we consider a co-cycle, right, we had to do it with triangulations and all. So we know how to, I mean, we have all the machinery to do it. It's just that then when you go to the weak to group on top of this, you have labels everywhere.
Yeah, it's a lot of work.
It's a bit of a, it's a bit messy, but
yeah. So as soon as you only have strict groups, you don't have to care about the coherence condition. As soon as you turn the coherence condition on, you have like pages to verify the coherence condition. I understand that. So I worked through this for a long time. So at least in my case, in the case I'm at, I found out that the triangle picture is much easier, and also have an explicit formula for higher groups. Where you were just asking, right? So it's in one of the appendix that I sent to you. So I think it's the second paper in one of the appendix. There is a very explicit formula.
Oh yeah, no, I think I know. Yeah, I guess I meant by explicit model, I really meant something. That you could really condense matter, like something you could almost express with polymatrices or something like this, like a bit like, I mean, we cannot, because we know how to define explicit models, but something like very, very explicit in terms of,
yeah.
Well, so I guess more physical, something that you can then relate to something a bit more physical.
You mean that, but I guess at least for high.
I'm sorry, I don't want to intervene in your discussion, but Alex, yeah, I was about to say if you can share. Would you also paste your slides, a PDF of your slides in the chat?
Yeah. Do I have to? Okay, let me stop sharing and I can open the chat.
By the way, so would it be okay for you to go to the discussion session 4 after the talks?
Yeah, that's fine.
Okay, perfect. If it's too complicated, it's no problem, but I think usually people do appreciate having slides.
Yeah, it's done now. It's just uploading. It's on slides, so it's a very big file.
Okay.
Thank you very much. It's indeed very helpful.
So here, could you go to full screen?
Yeah.
Okay, that's perfect. All right, welcome back. Our next speaker is Alex Bullivan, and the title is a categorification of the tube algebra. So Alex.
Okay. Thanks a lot for having me. It's a real pleasure to speak at this conference. So today I'm going to talk about a categorification of a lot of the ideas that were presented by Clément. And in particular, this is work in collaboration with Clement plus some upcoming work. Okay, so in 2+1 dimensions, particularly in the non-chiral setting, we have a pretty well-established collection of ideas, which can be summarized by the following commutative diagram. The idea is, given the data of a unitary spherical fusion category, then we have an algebraic construction called the center, which associates to this algebraic data an anion theory, which can be collected in terms of a modular tensor category. Now, as well as this kind of algebraic setup, we also have the kind of more classical condensed matter theory perspective. By using string nets, we can define a topological lattice Hamiltonian model, which I'll define briefly, but it's along the lines of what Clement was discussing. And the topological excitations in this theory are exactly described by this anion theory constructed by the center. So that's what I mean by this diagram commutes. Now, whenever I think about an anion theory, in particular modular tensor category, the kind of ideas that I have in mind are, given some space-time evolution for some topological phase in the 2-disk across times, this is a space-time of the 3-disk, then really my modular tensor category is a collection of rules that allow me to decompose some arbitrarily complicated space-time evolution into simple building blocks that are nicer to evaluate. And then I can compose them vertically in order to calculate my space-time evolution. Now, from this perspective, what my modular tensor category does is it collects as objects configurations of anions in the 2-disk, and the 1 morphisms correspond to isotopy classes of space-time evolutions, i.e. their world lines. And in particular, modular tensor category is braided and monoidal, and the monoidal structure tells us how to horizontally compose these blocks, whereas the braiding allows us to discuss the braiding of anions in the space-time. Now, what I want to talk about today is a lot less understood, at least for me, and this is the topic of non-chiral 3+1D topological phases of matter. So in this setting, it's conjectured that, well, at least a large collection of these models have a nice algebraic framework given by unitary spherical fusion 2 categories, as defined by Douglas and Reuter quite recently. And to this kind of data, again, we have a notion of center, which should give us what I'm going to call an extended anion theory. And by extended, what I really mean is that the excitations in this theory are no longer going to be just point particles, but they're going to be extended excitations like strings or loops, like in Clement's talk. And what we want to do is we want to understand some categorical package, which I'm going to call a modular tensor 2 category, as some nice way of discussing and describing this kind of physics. Now, recently, with work of Kong and Yuntian, I think we'll be talking about this later this week, they were able to compute the center for a given model, so-called digraph-Witten theory, with a spherical fusion 2 category, and they gave a nice description of it. And in today's talk, I actually want to talk about the other side of this diagram. So given some notion of topological lattice model, how can I understand the topological excitations and their relationships to an extended anion theory? And the way that I propose to do this is through what I call a categorified tube algebra. So before I get into the details, I want to describe roughly what I think of when I think about a modular tensor 2 category. I've put this in brackets because it's not a definition that we understand well or we really have a firm understanding of. But roughly speaking, there should be some kind of braided monoidal 2 category equipped with some extra conditions. And the extra conditions should be things like duality and some notion of remote detectability, i.e. an ability to detect our anions using topological processes. Now, when I want to do this, when I thought about a modular tensor category, I thought about decomposing my space-time into local chunks. In this setting, what I want to do is define a collection of rules that allow me to decompose the Hilbert space that this 3+1D theory applies to a 3-manifold, possibly with topological excitations within. I want to be able to decompose this into tensor factors and then describe this in a categorical package talking about local moves on these tensor factors. Okay, so when I just start saying that I want to decompose this, if I start by thinking about the Hilbert space of this 3-disk with a topological open string, for instance, in it, then the way that I want to package together my modular tensor 2 category is that I want to say that the anion, or I want to say that the point particles correspond to not just anions, but they're actually going to be anionic point-like states which exist in a gapped boundary condition for this three-dimensional Hilbert space. Now, rather than isotopy classes of Wald lines, the one morphisms, I think, should correspond to a Hilbert space of the 3-disk with open string excitations within it, possibly terminating on these gap boundaries. And the isotopy nature, or the topological nature, comes in the 2 morphisms, where we think about the 2 morphisms of being the space-time evolution, and this should be some kind of isotopy classes of string world sheets. Now, I said that this was monoidal. Again, the monoidal is this horizontal composition, and the braiding is what allows me to talk about under and over crossings of these string excitations, as well as braidings of their world sheets. So the kind of things that we want to be able to describe in this framework, at least a simple question, would be if I had a configuration of 2 closed loops embedded in the 3-disk, then I could consider a space-time evolution where I pass one loop through another. Think about blowing smoke rings through each other. And as I evolve this process, these world sheets define a knotted surface in the 4-disk, and we expect the amplitude for this process to only care about the isotopy class of this world sheet in the 4-disk. But another motivation for breaking our Hilbert space into these local tensor factors is that, unlike point particles, our loop-like excitations can also appear in links. So if we thought about closed loop excitations, we could think about a configuration where we had 3 loops all being threaded by another loop-like excitation. And again, we want to be able to describe the space-time dynamics of this process, such as braiding, as well as fusion while they're linked. And more generally, we could think about some arbitrary, horrible collection of links, but we'd still want to be able to describe their space-time evolution and their physics to describe the topological phase. Okay, so coming back to this idea, I want to begin by talking about Hamiltonian models for topological phases of matter, and in particular, what I'm going to call a topological lattice model. And this is going to be the building block for everything I say from now on. Okay, so this follows almost identically to what Clement was saying. And so what I'm going to say is that a topological lattice model is a collection of rules which for every oriented D-manifold sigma equipped with some discretization, i.e. some triangulation with some extra structure. And what it does is it defines for me a finite dimensional Hilbert space, which is just the free vector space over some classical field configurations, as well as a local Hamiltonian. So this Hamiltonian is going to be a sum of local operators, all of which have support in a local ball surrounding, say, a vertex of my lattice. And in the following, I'm going to assume that the local Hamiltonian operators satisfy the following algebra, which is to say that they are commuting with respect to a given ball, and they mutually commute as we spatially vary the terms. Now, in order to make our theory topological, what I'm going to do is I'm going to equip my lattice model with some extra structure, which is a family of unitary isomorphisms. And so given this Hilbert space, my Hamiltonian, this is a gapped Hamiltonian, so I can define a ground state subspace for a given triangulation of a manifold. And I'm going to say that if I have 2 discretizations of the same manifold, which agree on the boundary, then I'm going to equip my model with some knowledge of a unitary isomorphism mapping the ground state of one discretization to the ground state of the other discretization. And I really want to think about this as some form of symmetry of the ground state subspace. So it's going to satisfy some commutativity property with respect to the Hamiltonian operators. One thing I will note is that if I introduce manifolds with boundary, a priori, I'll always consider open boundary conditions. So the Hamiltonian constraints never act on degrees of freedom on the boundary, only on the interior of the manifold. Okay, so I've defined very briefly what I mean by a topological lattice model. Now, at the beginning of my talk, I was promising to talk about the excitations. And how I want to talk about the excitations is through what I'm coining the categorified tube algebra. Okay, so an algebra can be defined quite generally. So given a monoidal category C, an algebra is a pair consisting of an object and a morphism from A tensor A into A itself. And this satisfies some condition, which you can roughly think of as associativity, what it means to be associative inside a monoidal category C. Now, in the following, I want to talk about 2 algebras, or categorified algebras. And in analogy with algebras, I want to say that given a monoidal 2 category B, a 2 algebra is going to be a triple of an object a one morphism, just like in the algebra setting, but now I want a two isomorphism, which weakens this associativity diagram. And these two isomorphisms are required to satisfy some coherence data, which you can think of as relating the different ways of composing four copies of the object. I think I will note here that I'm going to use two category, but sometimes it might be by category, but I'm just going to use two category generically.
Excuse me, I have a question here. So a different object, is that correspond to different algebra? So this category is a collection of algebra. So different object is different algebra. That's kind of this way.
Kind of like it's so rather than thinking about a collection, it's just it's something I can define within the context of the category. So it's just a monoidal two category, but within this I can define a notion of two algebra whenever I have a triple of this data. Is that okay?
But my question is that you have object, but you have different object. Is that different object correspond to different algebra?
Yeah, a different object corresponds to a different algebra completely.
Okay, yeah.
So each choice of these triple defines a different algebra. Okay, and so in particular, the categorified true algebra I'm going to define is going to be a two algebra in the symmetric monoidal two category of vector module categories. So this is just the higher, if you think about an ordinary vector space as being a module over, say, the complex field, then I'm going to say that a two vector space is going to be a module over the category of vector spaces. Okay.
Sorry, with respect to that definition, why are you calling it an algebra as opposed to like a semi-group or something, like a weak semi-group?
Yeah, so we could call this like some kind of pseudo-monoid in a two category, because in the rest of my talk, I want to use the term algebra rather than pseudo-monoid. And so you could think about this as a pseudo-monoid, or everything I'm going to do is going to be linear, which is why I'm secretly calling it an algebra.
Okay, thank you.
Okay, now the underlying idea of the categorified tube algebra is very similar to what Clement was talking about with the tube algebra itself. And so what we're going to do here is, given a topological lattice model, we can define a Hilbert space to a three manifold, and using a technique very similar to the tube algebra, what we're actually going to do is we're going to, using the data of my topological lattice model, I want to define a two vector space to a two-dimensional manifold with boundary. And the idea here is that a two vector space in the rest of this talk is a semi-simple abelian category, or equivalent, you can think about it as the category of modules for a semi-simple algebra. And so using this notion, I'm going to define a two vector space. And then given this two vector space, I'm going to form a product and a two algebra internal to the category of two vector spaces. And similarly to what Clement was saying, the reason I call it a tube algebra is that it's based on this product will be based on the idea that given a pair of cylinders, I can glue them along a common boundary, and then I can use some orientation and boundary preserving diffeomorphism to shrink this union back to a single cylinder. And then what I'm going to do in the last part of this talk is explain that or motivate why I think that this extended anion theory is nicely captured by the representation theory of this two algebra. Okay, so let's begin with this idea of a two vector space for the cylinder. So given a 3+1D topological lattice model, I can define a Hilbert space, and in particular, a ground state subspace to any given three manifold. And so what I'm going to do is, given this three manifold equipped with a triangulation, and I'm going to not draw triangulations because otherwise it gets complicated, but let's assume that everything is equipped with the choice of triangulation. And this three manifold, I can really think of as being S1 cross the bigon. So bigon is kind of a two disk, thinking about crossing S1 into the plane. So using this ground state subspace, what I can do is exactly like in Clement's talk, I can define a finite dimensional associative star algebra inside the category of finite dimensional vector spaces. And in particular, these three conditions guarantee that this algebra will be semi-simple. And the way that I do this is, given the tensor product of these ground states, I pick some product state, and I can think about gluing this cylinder in, well, this manifold here inside this other one, And in order to do this, in order to glue the states, what I do is I have to say that the boundary condition on the exterior of here is the same as the boundary condition on the interior. And so I can match these two manifolds. And so if these field configurations align, then what I can do is I can compose these, and in some sense, I'm defining a state on the Hilbert space defined by gluing this manifold inside another one. So I'm defining a state on these glued manifolds. And the reason that I've colored the gluing seam in yellow in this picture is that a priori, if I start off with some state in the ground state here and the state in the ground state here, there's no reason when I glue them that the Hamiltonian constraints, or these Hamiltonian operators, will be satisfied in a local neighborhood of the gluing seam. I've just not added this data in. And what I want to talk about is ground states, because this is where these topological lattice models are particularly prominent. And so what I can do is, using the fact that my Hamiltonian is formed out of projectors, I can project any given state which is excited into a ground state. And so what I do is I project this state on the glued manifolds into the ground state subspace. And then, using the fact that my theory is equipped with this family of unitary isomorphisms, I can again map some state on this triangulation, which shares the same boundary as this one, and they're both the same manifold. I can define an isomorphism which maps me back into a state of this Hilbert space. And I'm going to say that the algebra product is given by making sure that this diagram commutes. So it's just given by the composition of these maps. Okay. Now, using the fact that this algebra is finite dimensional and semi-simple, what I can do is I can define a two-vector space, i.e. a semi-simple abelian category of the cylinder, which, if I think about the boundary of this manifold, it's two copies of the cylinder, its outer boundary and the inner one. Then if I take the category of, say, right modules for this algebra, then I can define a category, and this category in particular is an example of a two-vector space. Okay, so now I've explained how to define a two-vector space to a cylinder. How do we define a categorified product? And in the following slides is kind of the manifold I was drawing was S1 cross the bigon, but I think that the diagrams get far too hard for me to draw if I keep keeping this S1 in. So I'm going to remove a copy of S1 in the following to make the diagrams easier, but it doesn't change the ideas. Okay, so if I thought about the tube algebra, if I thought about this process considering a bigon, not this kind of, I call it the double skin barrel, then what we do here is, if I calculate the category of right modules for the algebra, then this defines a two-vector space to the line, to the interval. Now, given any module for some semi-simple algebra, we can always think about this as a subspace of the regular representation. So we can use this ground state subspace of the bigon in order to define our right modules, and up to isomorphism, every right module would be some sub-Hilbert space of the ground state Hilbert space of the bigon. So this is what motivates this diagrammatics. And what I can do is, given two modules, so these are both vector spaces, I can identify field configurations on these boundary points in order to kind of glue them together in some sense. If these field configurations don't match, then I map those to the zero module, the module defined by the zero vector space. Now, when I glue these together, this isn't canonically a right module for the bigon. If anything, it's not even a manifold in the classical sense, because we have this pinching at the point. And so in order to define a right module out of this data, what we do is we make the following observation. If I'm given the ground state subspace of the bigon, but here the left edge is created out of two line elements, then this right edge is a single line element. So it has a natural action of the bigon algebra on it. So this is a right algebra for this bigon Hilbert space. But on the left-hand side, I can glue along this seam. So I can identify this edge and this. And so what I do is I take these Hilbert spaces and this one, and I glue them together. So I identify their field configurations and apply the Hamiltonian constraints along the seam. And now, because this is a right module, I, in the category of modules, can just define some isomorphism of right modules to go back to one of the one of the modules, which is a subspace of the regular representation. And when I'm defining a 2 algebra, it's not just enough to define a product, but I also need some notion of associative up to isomorphism. Now, using this lattice interpretation, or this kind of topological lattice model interpretation, we actually have a really nice option for the associator that pops up naturally. And so if I think about this manifold here, I could think about this as one form of the associate, like one choice of bracketing for the product on 3 objects. And so I compose 1 and 2 by gluing this chunk of space here, and I compose 1, 2 with 3 by gluing a chunk here. And the other associativity brackets is given on the right-hand side. Now, because these are interpreted as ground states of the 2 disk, then I naturally, these 2 discretizations are just changed by a boundary, a triangulation change in the bulk, right? There's nothing happening on the boundary. And so I can use this family of these unitary isomorphisms to relate the field theory here to the field theory here, the Hilbert spaces. And in particular, the composition rules, which come from some underlying TQFT description for these triangulation changes, guarantee that this rule is satisfied for higher order coherence relations. So this higher order coherence that I didn't define is automatically satisfied when we define this 2 isomorphism like this. Okay, so in Clement's talk, he was talking about topological gauge theory with a higher group, but also he mentioned the finite group case, and we can apply this construction quite nicely in this setting. And in particular, what we find is that if we calculate the 2 vector space of the cylinder in this topological gauge theory of finite group, and then what we find is the following multi-fusion category is our 2 algebra. And in particular, the objects of this category are given by finite dimensional vector spaces graded by a set of elements that look like this, which are actually the morphisms in the conjugation groupoid. And so we think about it as a vector space with a subscript. The morphisms in this category are grading preserving linear maps, and the 2 product is associative, and the product is given by basically if G prime is the conjugate of G by H, then we just take the tensor product of the underlying vector spaces and define the new grading like this. And if this condition isn't satisfied, then we define this to be the 0 vector space, which exists with no grading. It's like 0 in the group algebra. Okay, so in the previous slide, I said that associated to the cylinder in finite gauge theory, I said that the category was multi-fusion. So I'll be honest, I haven't quite proved yet that this construction canonically always gives you a multi-fusion category. I know for gauge theory and higher gauge theory it does, but I'm still ironing out the proof. But roughly speaking, I conjecture that this 2 algebra is always actually a multi-fusion category for any choice of 3+1D topological lattice models, as I defined previously. And the idea here is that this should really follow from some categorification of an inner product structure. And this is because we should really be talking about 2 Hilbert spaces, not just 2 vector spaces. And we can discuss this in the questions if people are interested in this. And for the rest of the talk, I'm now going to assume that this is true. So in the final part of my talk, what I want to do is I've defined this categorified tube algebra for the cylinder. And what I want to do is I want to look at the representation theory of this and try and relate this to things that I understand in lattice models, and in particular, trying to understand extended anyonic theories. So what I can do is whenever I have an algebra, it's quite well known that if you have an algebra, you want to study its category of modules. And so a module is just some vector space which admits an action from an algebra. In a similar vein, we can define module categories for a 2 algebra. And we can think about this as you have a category, and this is equipped with a, if we're doing this in 2 vectors, it's going to be a linear functor plus some additional coherence data. And we think about this bi-functor as being a map from our algebra tensor over this category into itself. So we have an action functor. And we can collect this category, these module categories into a 2 category whose objects are module categories. The morphisms are module functors, which are just functors between these categories satisfying some relationships, ensuring like consistency with respect to this action, and 2 morphisms and natural transformations, again, compatible with this action and some other data. Okay, but what we want to do is, if I want to relate this to physics, I want to give a more concrete representation or concrete description of this. And so 2 works that I particularly recommend if you're trying to think about these things is the work of Douglas and Reuter, and the work of Goethe and Johnson-Fried, were both really nice areas for me to get into these things, as well as like the reference inside. So like if you want a more established references, I'd go with those. Okay. So yeah, okay. So roughly speaking, we defined what an algebra is inside a monoidal category. And so if we're assuming that this category is multifusion, it's monoidal. And so it turns out that modular categories for this multifusion category up to equivalence are described by a category of modules for a separable algebra in this category. And you can think about this as a generalization of semi-simple algebras, where you can define all of the modules in terms of idempotence within the algebra. Okay, now given a pair of modular categories defined like this, in a 2 category, we don't just have a collection or a set of morphisms between 2 objects, but instead we have a category of morphisms. And so in the setting, we call this the Hom category. And what's also nice to show is that the category of the Hom category for mod A and mod B, where these are separable algebras in here, is given by the category of AB bimodules in this multifusion category. So looking at these references, you can make these ideas precise. And before I give like a nice description of how these ideas relate to the physics, I just want to make an observation. So going back to my 2 vector space, I want to describe 2 nice ways in which you can define the morphisms in this category or 2 vector space. Now, one is that if we have some Hilbert space of the bygone as like some kind of regular representation, then if we change the triangulation in the bulk, you can easily show that this is an intertwiner for the right action of the algebra. And so this defines a morphism in this category. So internal triangulation changes is a morphism here. But the one that we'll use a lot next is that if I'm given some module and I'm given the ground state subspace of some manifold, which on the right-hand side, I can match with the left-hand side of my module, and on the left-hand side, it can be whatever you want, really, then actually I can define an intertwiner by gluing a state from this Hilbert space on the left-hand side of this module. And it's this idea that's going to allow us to relate this categorified tube algebra to ideas in the excitation spectrum. Okay, so whenever I have some AB bimodules, there's a nice way of defining this in terms of an algebra, and in particular modules for an algebra. And so I'm going to define an algebra whose module theory defines AB bimodules in our multifusion category. And so I'm going to call this A/B. So this is a morphism between mod A and mod B. And what I can do is I can say that this algebra as a vector space is the direct summand of the Hom spaces in my module category. So if this is a abelian category, then it's Hom spaces of vector spaces. And so I can form a vector space just by taking the direct summand over the collection of objects in this category of this vector space here. And so we just pick a representative set of objects and form this. Now, what I can do is, in this setting, is, so let's think of it. So if I take A tensor X tensor B, then I can define some right module as in the following. And if I want to define a Hom into some right module Y, well, what I can do is I can define some state which I can glue such that once I've glued it to the right, the corresponding right module is isomorphic to Y. And it's this idea of this state that we're going to use to talk about these bimodules. And so in particular, if I take a triangulation of the 2 disk and the Hilbert space on this, then what I can show is that this Hom space, so one of the factors of this direct summand, this Hom space is a subspace of this ground state. So we have a nice identification of this. And then this intertwiner or this morphism from here to here is nothing more than a state in this Hilbert space. Now I did this in the lower dimensional setting, but the same applies. But the same applies in our 3+1D setting, where in this setting it's slightly harder to see, but in essence we find that the elements of this Hom space are just given by subspaces of the ground state of the annulus cross the interval. And I'm going to draw the states like this. So if I have an algebra, I need to define a product, and the product goes a little bit like this. So given a state here, so given one of the states in the cylinder and the annulus cross the interval, then what I can do is I can define the algebra product induced from the previous as an interpretation on the lattice, on our topological lattice model. And what we do is, I've chosen this, so this right state is glued inside this left one by identifying these cylindrical boundaries. This defines a state here. But the problem is that in my topological lattice model, all I told you how to do was change triangulations which preserve the triangulation of the boundary. Now, this is where the notion of these kind of separable algebras comes in. So my separable algebra is a morphism from A tensor A to A, satisfying some additional constructions. And I can think about this again as a state. And it's a state of this funky looking manifold. Which I suppose, is it the suspension? Anyway, it's of this manifold here. And so if I have a notion of algebra, I've defined one of these states, which makes this product make sense. And so what I can do is using this idea, I can define the algebra product by gluing one inside the other one, and then gluing these states on the top and bottom. And so if I glue, so this edge is identified with this cylinder, and so it goes to the top. And then once I've glued it on, then I have my triangulation changes, which allow me to deform a state here into a state of the original form. And it turns out that you can argue very nicely that this is in one-to-one correspondence with the algebra required to define the bimodular objects. Now, what we want to do is we have this new algebra. It looks a lot like the tube algebra that Clement was discussing. And what we want to do now is relate this to the excitations in the theory, akin to what Clement was talking about. So what I could do is, if I'm given a copy of, so this is D2 cross the interval, I could think about having some open-ended string excitation in the theory. And so the idea is that in a local neighborhood of the string, we can tell its presence by a violation of the Hamiltonian constraints. And what we do is we say that if I have a gapped system, in particular these topological models are going to be the fixed points of my theory, then the correlations of the theory, the entanglement between some region A and region B, is in essence localized on the boundary. And so what I can do is if I take a local neighborhood of the string where the Hamiltonian constraints are violated, then what I can do is I can introduce a new boundary, and this boundary in some sense is defining the correlations between the interior of this excited region and the exterior. And so I can map problems about understanding these excitations into boundary theories. Okay, now, as in Clement's talk, just having a boundary theory is not enough, right? We need to decompose these boundary conditions with respect to some symmetry in the same way in gauge theory, you look at the particles as being representations of the gauge group. It's about transformation properties. And so what we're going to do here is we can interpret, is we say that if we have these gluing rules, then what
Alex,
yeah.
Sorry. So, Xiaogang, you want to ask a question or you want to make an applause? I was just unsure because, did you want to ask a question? Okay, if not, sorry for interrupting. Yeah, Alex, please continue. Sorry.
Any questions? I don't know if people okay. And so So what we can do is we can convert our statements about trying to understand these topological excitations into ideas about boundary conditions. But what we want to do is we want to find some symmetry in order to decompose these boundary conditions. And the natural symmetry we have in our topological models is length scale invariance. And so what we can do is, given this manifold here and classifying these boundary conditions, we can interpret this algebra product of stacking these cylinders inside and then deforming the triangulation. But we can think about this as a process of adding more space or performing a renormalization group action and then deforming it back to itself. So we're looking at an action of renormalization of this boundary by gluing these states. And in particular, this is exactly what we want when we want to talk about topological excitations, because these really should be excitations which are measurable at all length scales. Our topological theory exists in the low energy limit where our metric degrees of freedom vanish. And so this is a good principle for characterizing topological excitations. Now, using this idea, we say that we can associate a module for this algebra, and we can think about this as defining a length scale invariant Hilbert space for a string excitation. And what we're really doing here is we're saying that we're classifying topological strings, but because we're removing, in essence, all of the local data with this renormalization process, it's really an equivalence class of topological strings up to the introduction of a local excitation. In a similar way, this idea of we had some separable algebra, well, what this does is you can, by using some really nice arguments, you can show that the separable algebra corresponds to two things. First part of the algebra is the object, and that defines a way of defining gapped boundary conditions on the edge of this manifold. And the algebra property is telling us about the renormalization or how to change the length scale of the theory stuck on the boundary. And so we can interpret the category of modules for this as describing anyons which are pinned to a possibly anomalous boundary condition of our spatial manifold. Now, using these ideas, if we have a two category, we can think about what the composition of one morphisms is. So if I think about a one morphism as being some Hilbert space with a string excitation in it, and I can think about the composition as stacking two chunks of 3D space together. And then the two morphisms actually give us a collection of rules to renormalize this. So here we've introduced a new boundary, which is kind of no longer the boundary as such. And the two morphisms in our category tell us how to get away this. So how to go from two strings with a kind of fictitious boundary, and then by renormalization style arguments, we can remove this boundary. Okay, so what I've done so far, or hopefully I've argued to some extent, is that if I have this category mod of the circle, then I've got some way of talking about Hilbert spaces of the 3-disk with possibly open strings inside. But at the beginning of this talk, I said that my 3+1D topological order should have some kind of monoidal structure, this horizontal composition I've not told you about, as well as some braiding structure, allowing us to define under and over crossings of these lines, and also their world lines. Well, in order for us to understand this, I'm just going to pose an observation and then some questions that I'm still trying to work out. So it's well known that if I have some category of modules and I want it to have fusion and braiding structures, then I define a Hopf algebra. Well, in our setting, if we have a topological gauge theory, I defined with this multi-fusion category associated with the cylinder in topological gauge theory, then what it turns out is that this category can be equipped with what's called a quasi-triangular Hopf category structure. And if you want to see more about this, I fully recommend the thesis of Neutral, which I think is called Representation Theory of Hopf Categories. And what this really does is this categorifies the usual ideas of Hopf algebras in a very nice way. And in particular, if I have some multi-fusion category in which I can equip it with a quasi-triangular Hopf category structure, then its category, well, its two category of modules actually becomes braided and monoidal. And additionally, the Hopf part means that it has jewels. Now, there's a very nice and easy way to map, to apply a quasi-triangular structure to this multi-fusion category. And if you do, if you calculate the representation theory as well as these braiding and monoidal structures, then what you find is we actually reproduce the result in Kong, Tian, and Zhao's work, which I think we'll be talking about on Friday, where they calculate the center of G-graded 2 vector spaces with cohomology, and you can show up to some equivalence of braided monoidal 2 categories that this is really the same thing. Now, an open question that I don't know how to answer quite yet, but I'm working on, is can we canonically put a quasi-triangular Hopf category structure, or in principle a weakened variant, on this multi-fusion category defined by a 3+1D topological phase? And if we can, there's a nice relationship between topological lattice models in 3+1D and spherical fusion 2 categories. Can we use this canonical assignment to verify completely that the center of this corresponding fusion 2 category is this braided monoidal representation category coming from the topological lattice model? And so this is what I'm working on at the moment. And before I end this talk, I'm just going to have one more slide. And this is a kind of dimensional reduction argument. And what it turns out is that given a 2 category, well, this kind of 2 category of module categories, I can define this notion called the dimension. And the dimension is a braided monoidal category consisting of pseudo-natural transformations of the identity 2 functor and modifications between them. And it turns out, in general sense, for any module category of a multi-fusion category, this is the same as computing the Drinfeld center of the multi-fusion category. So you can show this correspondence. And it turns out that if I think about what the center of this category is, using similar lattice model-induced ideas, then what I can show is that if I thought about the tube algebra for the torus across the interval, which is what was discussed in Clement's talk, then what I actually find is that the Drinfeld center of this has a very natural interpretation as corresponding to a category defining loop excitations in the theory, possibly with some threading between them. And by here, I've put this BR above to say braiding, where as it comes from a Drinfeld center construction, this additionally has the description of the fusion and the braiding of these loops while coupled to this background loop. And the motion group of this is often referred to as the linear necklace group. And I think that's everything that I want to talk about today. So thank you for listening.
Thank you, Alex. Thanks. Are there any brief questions? So let me recall that we're going to have a possibility to discuss with Alex after the talks. So he will be in the discussion session 4. So it will be after the talks around 6:30 European time. Thank you again, Alex. And now we have a break till 4 o'clock. We resume at 4 with the mini course of Xiaogang.
Hi, Alex. Really nice talk. Thank you very much.
Thank you.
So I have a simple question. In the when you glue in the higher dimension, when you glue 2 things, you need to glue the surface. Then you need to say, okay, I need to supply additional projector at this gluing surface.
Yeah.
In higher dimension, you also have this intersection of 2 surfaces, this line or this point you mentioned.
Yeah.
And so what do you do there? So that's one lower dimension.
Yeah, so in essence, how you can think about this is I'm trying to define what the fully extended TQFT assigns to a codimension 2 of space manifold, is the kind of fully extended jargon of what I'm doing. And so what I did is when I had these kind of horrible, maybe I can even reopen the slide.
Yeah, you can share your screen.
Yeah. Okay, so this is the secret, and this is what took me a long time to understand, actually. So I think, what's it doing? I'm sorry. Yeah, okay. So here, so if this is a 2 + 1D picture.
Yeah. This is a. Oh. Okay. Yeah. Yeah, that picture exactly the where's my question is.
Yeah. I'm just getting it back. Okay. Right.
Yeah.
So this is 2 + 1D. So codimension 2 of space is the point. So I identify the point. And so I glue the point. And now the point is that I need what's often like I used to call it unthickening. So I need some rule which allows me to take this kind of very degenerate manifold. It's not really a manifold in the classical sense, and I need a way of unpinching it. And the way that you do this is quite subtle. And it's inspired by the fact that if I have a module for an algebra, if I do module tensor product over the algebra times the algebra, then this is isomorphic to the module. So you have this kind of trivial action. And so what you do here is given these modules like this, it's not really a manifold. Now this ground state subspace, so I can identify this left boundary with the right boundary of this. So I have some ability to glue along it. And the right boundary of this is a module for my bigons. I can think about the action of gluing a bigon on the right. And the easiest way to see that this will give you a right module for the bigon after I glue them is the fact that these gluing operations are associative. And so if I glue a bigon on the right and then glue it onto this is the same as gluing it to this and then applying a bigon on the right, using this kind of left and right.
There are some details here. First, on this boundary, you have a so-called free boundary condition, means no constraint, no projector.
So the left boundary is no constraint, and the right
this boundary
is such that it's a module. So it has to be closed under the right action.
Okay, but usually when you have a bigon, you have no constraint on the boundary. That's correct?
Yeah. So I just have the free field configuration. So I think about my Hilbert space as the direct summand of all field configurations on the boundary, the Hamiltonian mixing.
Yeah. And then on this boundary, you have this dot. So do you do something around this dot?
Sorry,
can you see my pen? Can you see? Yeah, this is a.
Sorry. Yeah. Okay.
Yeah. This is dots. So do you do anything special on this dots?
No, nothing at all. Nothing at all.
I see. So it's just symbolic. Okay.
Yeah. It's there to show that this, to show this left-hand side is 2 intervals which glue onto here.
I see. Okay. So therefore, on this boundary is a kind of a so-called free boundary condition, just a degree freedom, no constraint.
Yeah.
Similar boundary, you have a similar thing. Then the gluing structure, the gluing is actually identify this degree freedom.
Yeah. So
then here you do something extra. Is that you also do no, I don't see here. But when you glue these 2 boundaries, then you apply some kind of projector on the gluing boundary.
Yeah. Right. So
what happened at this special point? This point.
This point doesn't get acted on via the Hamiltonian constraint ever, because what happens is when this point goes over here, it's on the boundary.
I see.
It's much simpler. If I assume that my category was fusion, then a lot of these subtleties disappear because there's a one-dimensional Hilbert space on the disk, right? For any given boundary condition. Some of these ideas here I've left in because if you think about particular higher gauge theories, then you have to be much more careful. They're like multi-fusion category, and the disk can have higher dimensional spaces.
Okay. So I see. So only on this boundary, and also on this part, you have a projector.
It's on these these edges. So you have these
on those edges, you have projectors. There are no projectors. Okay. Then that's how you do the gluing. Okay. Thank you very much.
You into a state over here, just in a very nice way. And there's lots of.
Actually, this is a little bit maybe a little misleading because these 2 points, the same point. They should be together.
Yeah, it's hard to draw. I had these 3-dimensional.
You may want to draw this way.
And I had versions with triangulations, but it got too confusing to make it worthwhile using.
Okay. Okay, thank you very much. Yeah, it's nice to know you because I only know you from your paper on the archive.
yeah, and likewise,
this is a very special meeting. People in different community kind of start to meet. It's a interesting, exciting.
If you ever have any questions or anything, please feel free to send me an email. I'll always send a nice reply.
Okay, thank you.
Thank you.
Yeah, so over here also I have a continuous. So how do you connect it to? I guess these modules are flat connections somewhere in Clement's talk. So these bygons are group elements, and these the grounds the things in the bracket. They're modules.
So these are really triangulations, and then each of this is just like with some cellulation of some sort. And so the reason you want some cellulation is that it allows you to localize your field configurations in your theory. And so these ideas of gluing these manifolds along each other, if I did this in the smooth setting, I'd need tangent bundles and things like this. And so this discretized setting really allows you to very simply understand how to glue chunks of space without framing issues and define these diffeomorphisms. So it's like piecewise linear homeomorphisms between one ground state and another.
Yeah, I'm just saying that I try to match your modules and the Clement's modules. The modules in.
So if we go to this slide, I don't know why my computer's. If we go to this slide, then the modules over this are exactly the same as the modules in Clement's slide, or at least like in principle, this is the exact same operation, but it allows you to do what Clement was discussing for boundaries which have boundary, if you know what I mean. So in Clement's talk, he had the torus, and he was thinking about tube algebras of the torus cross the interval. Well, here...
You're only describing his space manifold. So in Clement's talk, the module really was the collection of flat connections on this manifold, right? Isn't it?
Yeah.
What you draw over here is just the manifold itself.
It's just about, so the idea here is that his flat connection story comes from defining some Hilbert spaces. And so these Hilbert spaces are defined by their flat connections. In this setting, I have a ground state Hilbert space, and this is defined by my topological lattice model. And so here I don't need it to be group-like, it just has to be any collection of degrees of freedom that defines a Hilbert space and a Hamiltonian obeying certain properties. But these flat G connection version of the story works identically. That's just one example of this.
Right. It's very explicit. It's a very explicit, how do you say, realization of this, right?
Yeah, exactly. So that's a explicit realization.
Helpful. Yeah.
But when you want to categorify, it's easier to maybe hand wave with how you glue things together rather than give the explicit examples. But in the flat gauge connection case, like it's very easy to do the explicit calculation for this, even with cohomology twisting.
Right. It has different collaterals.
Q-form gauge theory. You can do this, the like strict 2 gauge theory, you can do easily here, because there's a secret. If you do like strict 2 gauge theory, then you're basically doing algebraic topology, and you can steal lots of like functorial theorems. And so you can describe this process entirely in terms of like homotopy, like it's a homotopy of linear maps into the classifying space. But the weak case, I don't know how to do that analysis, which is why like the strict 2 case is much simpler.
Right. So I wish our model helps for your.
I think it definitely works.
for your non-strict case. I mean,
in the non-strict case, it definitely works. So the non-strict case defines a Hamiltonian of the form that we're talking about. And so this works as a model independent construction. So as long as you can define a Hamiltonian of that form, this construction is guaranteed to work. And the non-strict 2-group case, even with 4th order cohomology twisting, completely works on the nose.
Hamiltonian, how it works, that was another question I asked you, but maybe we should discuss in the break. I mean,
that'd be nice.
You need to have a break. Watch that on short counts. Okay, we'll talk about this later.
Yeah, thank you. Bye-bye.
Alex, can I ask a question?
Yes, please.
I have, I'm sorry, I just somehow missed a few slides during the talk. For ordinary, the classical tube algebra, you have a triangulation of the cylinder. You decorate it by, you decorate this 1 cells and 0 cells by the object of the fusion categories.
Well, it's like what you're secretly doing in the ordinary tube algebra. So it'd be really nice to discuss with you these ideas. So in the ordinary tube algebra, what you're secretly doing is you're thinking about, so given an object X, you're thinking about A star, so given an object A and X, if I want to braid, so X is in the center and I want X is going to be in the center. Maybe, can I open a white, so if I have maybe if I screen share, maybe I can explain this a little bit better. But maybe the idea here is that you could do like A star tensor X tensor A and then Hom into Y. And so you think about the ground side of the cylinder is an element of that Hom space. And so here what I expect is that so these tubes should really be the analog of this when I think about spherical fusion 2 categories, right? And so that's what I'm working on at the moment. And so it's
I see.
You define like a 2 module over some multi-fusion category defined in terms of these Hom categories.
So in the sense that you have a higher tube and you triangulate it, you decorate it by a higher fusion 2 category, right?
Yeah.
I see.
And there should correspond to Hom space within the fusion 2 category. There should be duality between either triangulation or an element of Hom.
Okay, so what I missed is that I missed a few slides, so I didn't know that. Have you worked this out completely, or?
Well, not the most general. So in the group case, so in the digraph Witten with cohomology twist, I've worked out absolutely everything.
I see.
In higher gauge, I've worked out 99.
Apologies, probably we can postpone the discussions to the discussion session, if you don't mind. So Xiaogang, thanks a lot for giving us, right? I think in the chat you already gave us the final version of your slides.
Yes.
So the final version of the slides is on the chat.
So is that my voice is clear?
Sorry?
My sound is clear? Oh, no.
Yeah, your sound is good.
Okay.
Right. Absolutely. So I think we are ready to start. So our next talk is the final lecture of Xiaogang's mini course. So Xiaogang, I give you the floor.
Okay, thank you. Let me try to get where we are last time. Yeah, this is a last lecture. We compute the quantum dimension. And so in the last lecture, we mentioned that we defined this so-called unitary fusion category. We say that this unitary fusion category is a theory, or you can say a field theory, that describe one-dimensional excitation, one spatial dimension excitation. Okay, so then this comes a question. If that's really true, means that can we really find a one-dimensional local lattice model such that this lattice model have an excitation which described by this unitary fusion category? The answer is no. So actually we do so much and for nothing. Oh, seems. So this abstraction to find a one-dimensional lattice model is called anomaly. So anomaly, so we say this unitary fusion category anomalous means we cannot find any one-dimensional lattice model which realized, which produce excitation described by unitary fusion category. Actually, it's not quite true that there's one unitary fusion category which is not anomalous, which is realizable, but that one is a trivial one. So any non-trivial one is not realizable. So the reason for this, actually, there's a motivation for this. Is this relation between remotely detectable and realizable, or another way to say anomaly free. When you say anomaly free, means realizable by the lattice model in the same dimension. So so there's a belief. This is conjecture. That there's belief that if every excitation can be probed by, can be detected by other excitation via some remote operation, then this category is realizable or anomaly free. And this remote operation is something like a braiding. Say, suppose we have a excitation here, and we want to use another excitation to probe it. We can just braid this second excitation around the first one, far away, never touch, never come close to the first one. So therefore, if every excitation can be detected by this way, then we say it's remotely detectable, or we say it's anomaly free. And now we see that in one dimension, we cannot do that because dimensionality, when you have 1D excitation, we cannot do this kind of braiding or maybe some similar remote operation. And so therefore, all the non-trivial unitary fusion category are anomalous, except the trivial one. And so therefore, there's no 1D lattice model realize this unitary fusion category. And then we believe that for any gap system, the excitation are always described by unitary fusion category. And only the trivial one is realizable. So therefore, in one dimension lattice model, we only have a trivial topology order. And this is again something we believe. There is no non-trivial topology order in one dimension. And this sounds strange because there's a lot of 1 plus 1D or 2-dimensional TQFT. They classify Fubini algebra. So there's many papers study that. So that kind of TQFT actually do not correspond to topology order in condensed matter sense because they are unstable. They are not a stable phase. And so the statement here is that this 1D TQFT or 2D TQFT are really correspond unstable, not really correspond to topology order. Non-trivial topology order only appear in higher dimension, not in one dimension. So in higher dimension, and we can still do fusion because we can put a higher dimensional excitation on a line, then we can do fusion. But then we can also do braiding. That's one extra thing we can do. We can also do braiding. And in particular, we have a double braiding. The double braiding is like a mutual statistics. We move this one excitation all the way around another excitation. It's called double braiding. And this double braiding in physics is called mutual statistics. So when you move one excitation around another excitation, you get a phase factor. Okay. So this phase factor is a theta ij, depend on this excitation I and j. So the theta ij is a phase factor mutual statistics between I and j excitation.
Sorry, Xiaogang,
Yes.
why do you restrict this product of our matrices to be only a phase factor? Why can't it be some more complicated matrix?
Yes, and so the reason is that this ij is assumed to be a simple object. They assume to be stable excitation.
Sure.
If they assume to stable excitation, so yeah, this became just a phase factor.
Well, why can't it be something more complicated, more non-abelian? Who knows?
Yeah. Okay. So here there's a little bit more non-abelians here. Let me explain.
Mm-hmm.
Actually, this phase factor is not just depend on ij, also depend on when ij fuse into something k. You know, ij can fuse into k1, k2. Then depend on this different fusion channel, the phase can be different. And that's only little bit non-abelian thing. So it's diagonal matrix, and there's no off-diagonal element. And so therefore, this phase factor actually have 3 index ij and k depend on the fusion channel of I and j.
No, I still don't believe you. I think Anton is right. Why can't a single anion appear with multiplicity in the fusion?
Yeah, they can, but this assumption is that ij are simple object. Here I assume
but k
ij,
doesn't have to be. You could have 2 copies of the same k, and then you could have a 2 by 2 matrix.
Oh
No?
yeah, sorry. Yeah, that's right. Okay. If a k is a several copy, yeah, then this can be a 2 by 2 matrix. Yeah, I'm sorry. Yeah, this is a let me see. And then this 2 by 2 matrix, it can be diagonalized.
Yeah, maybe you can still diagonalize. Yeah. So maybe in some basis it's still going to be like that. Okay.
Yeah. So so it's related to this thing that we talk about the topological spin. So this phase factor and topological spin are related in this fashion. So actually, if you know the topological spin, we know the mutual statistics. So actually, there's for the simple braiding, this is the R matrix. So I will not go into this in detail because time constraint. And just say there's R symbol, there's F symbol, and then there's a consist condition. And if you have N and F, we get the fusion category. If you have N, F, R, then we get the so-called braided fusion category. So that's the very simple way to understand this braided fusion category. And the braided fusion category is supposed to describe excitation in 2-dimensional topological order. So here, let's give you some example. Simplest braided fusion category have 2 objects, identity, trivial object, and E. They both have a quantum dimension 1. They both are boson. And this have a formal name. It's a repetition category of Z2. It's a symmetric fusion category of this rep Z2. And there are other thing like this. They have Samian model. We have 2 objects, both with identity quantum dimension, but the non-trivial object have a spin a quarter. That's a Samian, and this realized in the bosonic quantum Hall states. And then we have a Fibonacci topology order, where again also 2 objects. The quantum dimension is this Fibonacci number. The spin is 2/5. And this Z2 gate theory is what we discussed, the EMF. And we have the 1 fermion, and we also discuss string net. String net actually is a double Fibonacci. It's like a 2 copy Fibonacci together, and it's a Fibonacci and anti-Fibonacci. So this is like a double Fibonacci. The string net example we discussed. Okay. So the first example here is anomalous because this E particle cannot be detected by any other particle, either 1 or E. Okay. So we already say that the braiding is degenerate. Okay. And so this is characterized by the Milgrom center, or more generally E2 center. That is this E2 center is a set of anyons that have a trivial mutual statistics with everything else. Okay. If the only anion with trivial mutual statistics with everything else is a trivial particle, then this we say is a non-degenerate, or it's modular, or it's realizable, or anomaly free. Okay, so this Z2 center is trivial, is an anomaly free condition or realizable condition, and all these other, for example, are modular, and their Z2 center, Milgrom center is trivial, but this one, the Milgrom center itself, so it's non-trivial. So this one is anomalous, not realizable, and those are realizable. So this led to this conjecture that this unitary modular tensor category, where Z2 center is trivial, classify the two-dimensional topological order. But actually, it's not quite true. There's a little bit of mismatch here. It's actually this unitary modular tensor categories do not classify 2D topological order, but classify 2D topological order up to this invertible topological order. So there are some topological order whose excitations are trivial. So they call the invertible topological order. So invertible topological basically means that when you have a stacking A topological order and B topological order stacking together, you get a C topological order. Invertible one is that if A is invertible, that means you can find B such that their stacking give you C, which is a trivial, the trivial product state. Via stacking, you can obtain trivial product state. Then that's invertible. And invertible topological have only trivial excitation. They do not have a non-trivial excitations. Okay, and their topological partition is a phase factor. Okay, so using unitary modular tensor category only classify excitations, but the invertible one have a trivial excitation. So they can overlook that. But if you quotient out invertible one, then we believe there's a one-to-one identification. So so using this idea, we can get a list of unitary modular tensor category, which is also a list we believe is a two-dimensional topological order up to the invertible ones. And on this list, say we have this Z2 gauge theory, which is here. This line is a Z2 gauge theory, and the double Samian model we discussed before also appear here. And the double Fibonacci is here. This one is a stringlet double Fibonacci, and etc. Okay. So then we can apply this idea to higher dimension. So in higher dimension, we can also think about maybe we can classify topological order by classify their excitations. But in higher dimension, the excitations are described by so-called fusion N category. There's a higher category. So this fusion N category actually is a following. The object in the fusion N category corresponds to co-dimension one excitation. So here is a two-dimensional example. This string is the object. So that's a fusion 2 category. String is the object. Then the one morphism in the fusion N category is a domain wall between strings. So that's connecting two different strings. That's a one morphism, domain wall between strings. And there's special domain wall between trivial strings. And that's in physics we call a point-like excitation. Okay, this domain wall between same trivial string is a point-like excitation. And then, however, there is also a string excitation, which are connected to the trivial string. Actually, this is called condensation excitation and or descendant excitation. They are kind of trivial, and I will not spend time on that. And but this is one of a special kind of excitation. And this fusion category, fusion 2 category, actually already contain information for braiding, because we can we can do a vertical fusion. We can fuse two domain wall, and we can do horizontal fusion two strings. And the consistent condition between vertical fusion and horizontal fusion can generate the braiding of these point-like excitations. So the braiding is already contain the consistency of a fusion two consistency. Okay. So and as before, the unitary fusion n category and the topological order is not it's not just one-to-one related. It's their relation a little bit more complicated. To describe their relation, we can consider there's a map from a realizable topological order on the lattice to the fusion n category. And this map physically just means every realizable topological order have excitations, and their excitations are described by fusion n category. And that's basically generates this map. But this map is not subjective. So the image of this map is defined as a normally free fusion n category, it means realizable. The image of this map means those fusion categories are realizable by lattice model. The kernel of this map is happen to be invertible topological order. So therefore, up to invertible topological order, we can use this anomaly free fusion n category to classify topological order. Any questions? Okay.
Yeah, Alex, I'm not sure. Did you have a question or? Yeah, let's continue. If there are questions, please either unmute yourself or raise the hand. Thank you.
So so right now we try to use this fusion n category to classify topological order up to invertible one. Invertible one is pretty well understood. So up to invertible one, what is fusion n category, which can classify topological order. So here we see that we need to find a subset of fusion n categories. Only some special fusion n category can correspond to a realizable topological order. And so to find this subset is the following thing. Actually, when I say realizable, I'm using this so-called microscopic definition, using a lattice model to define realizable. And but when you try to find a subset, we are looking for some macroscopic properties, and which can apply to fusion n category. So you want to translate this anomaly free, defined microscopically to an anomaly free defined macroscopically, and we have did that. We have done that for the two-dimensional topological order. It's an E2 center. And I was told that this E2 center can also be defined on the fusion n category, but it's a physics things is more complicated, so I will not go into that route. So here to identify this fusion, this anomaly-free fusion n category, this special class fusion n category, which can be realized by lattice model, we use so-called boundary bulk relation. Okay. So we already say that anomaly or gravitational anomaly means that abstraction to be realizable. Okay. But the question is, what is this abstraction? Okay. To understand this abstraction more explicitly, we notice the following thing. Although this unitary fusion category describe a 1D excitation, in a sense, they kind of locally consistent, but they are not realizable, means that they are not globally consistent. So this not globally consistent means this anomaly. But there's still some consistency. And this local consistency ensure that actually this unitary fusion category can be realized at the boundary of a two-dimensional topological order. So that's really a boundary bulk relation. Okay. For example, yes.
Shagang, I have a naive question. So you say gravitational anomaly. Is it in some way related to the notion of framing that you
Yes, it's one of them, but what I have here is more general. So I will come back to this point.
Okay.
Yeah. So, but here, the gravitational anomaly have been studied before, and but here I'm really presenting a more modern point of view. I will review the old point of view maybe a little bit later. So here we say that not realizable means anomalous, but they are realizable as a boundary. Okay. For example, this Fibonacci fusion category, this phi became 1 plus phi. Actually, it's realizable as a boundary for this two-dimensional string net wave function. Actually, this string net wave function have a particular boundary, and the boundary excitation happen to be described as a unitary fusion category. So this really gave us this triangle. Actually, we already see this triangle in this morning's talk. That's given a unitary fusion two category, we have this wave function, which using this data, we can design a two-dimensional string net wave function. So this map to 2D wave function. And also this unitary fusion category also can be viewed as a description of a one-dimensional excitation. And the boundary of this wave function happen to reproduce this boundary, this 1D excitation. Okay. So from here, we can see that the different type of anomaly really correspond to different 2D topology order. So it's really that the non-trivial bulk topology order is related to the gravitational anomaly at the boundary. Okay. So in higher dimension, this idea we kind of propose this idea also works in any dimension. So in higher dimension, we have so-called the potentially anomalous topology order. Basically means a fusion N category. So in general, a fusion N category is it's not realizable, but maybe we call this anomalous topology, may not be realizable. Okay. And anomaly-free topology order means a realizable topology order. Actually, it's a boundary of trivial product states. Because when you have a trivial product state, the trivial product is not connected. You can remove the bulk. Okay, trivial product states the bulk can be removed, and you only have a pure boundary states. So therefore, the boundary of trivial product states means realizable at the boundary alone. So realizable at one lower dimension. Okay. So from here we can see that anomaly-free means their bulk is a trivial. Anomalous means their bulk is a non-trivial topology order. Okay. And there is again there's a conjecture. The holographic principle of topology order means that the boundary uniquely determine the bulk. Okay. So when you have a topology order with a boundary, actually if you know the boundary, then you know the bulk uniquely. Okay, so here we say that the boundary is a fusion N category. Okay, the bulk is anomaly-free topology order. Okay, so there's a connection between fusion N category and the bulk, but the bulk topology order also described by some kind of category, which actually is a braided fusion category. Okay, so this mathematically this principle means that there is a functor we call the Z1 center actually. The map the NA fusion N category to the braided fusion N category. And this braided fusion category actually is non-degenerate. So their bulk is a trivial. Okay, so this is anomaly free. Their bulk is a trivial. Okay, so this boundary bulk relation really tell us what is the gravitational anomaly. You know, before we say gravitational anomaly is something is abstraction to have a realization in the same dimension. But here we can say in more detail that the gravitational anomaly actually is almost equal to the topology order in one higher dimension. Okay. Similarly, this de Hoof anomaly or symmetry anomaly is SPD order in one higher dimension. This SPD order is discussed in the Zheng Chen Gu's talk yesterday. So therefore, using this boundary bulk relation, actually we can obtain the classification of anomaly-free topology order. Means that a realizable topology order in n dimension can be classified by the unitary fusion n category, which satisfy this condition, means they have a trivial bulk. Okay. And this trivial bulk is really anomaly-free condition or realizable condition. And certainly this classification is do not see invertible one, so it's only up to invertible one. Also, I want to say that there's another condition. This unitary fusion n category should include all condensation excitation. And this is important. This condition is pointed out by Galta and Johnson Fried. And I think Johnson Fried probably will discuss that this Friday. And so because gravitational anomaly is so important, so let's spend some time on anomaly. So usually gravitational anomaly is defined as an abstraction to have a nice path integral. Means that usually when you have a action, this action are diffeomorphic invariants. But however, using this action to define a quantum theory via path integral, this path integral measure is not diffeomorphic invariants. So therefore, this partition function may not be diffeomorphic invariants. And so that's what we call the gravitational anomaly. And this kind of gravitational anomaly is always invertible. So that means that like this Jacobian is some kind of non-zero complex number. So these anomalies are invertible. And that's a more traditional point of view of anomaly. And but what we have here is a more modern point of view of anomaly. We say that anomaly is the abstraction to have a realization in the same dimension. But however, even anomaly theory can be realized as a boundary of a higher dimensional theory. And in this case, anomaly is really correspond to topological order in one higher dimension. And from this point of view, we see that this anomaly is more general. And in particular, than in general, non-invertible. Because topological order in higher dimension, in general, not invertible. The stacking two topological order can never produce trivial states in general. And so therefore, so this more modern point of view really gave us more general gravitational anomaly, and in particular, non-invertible gravitational anomaly. The traditional gravitational anomaly, I think, may correspond to invertible topological order in the bulk. And so in the next, I'm going to try to using this idea of topological order in gravitational anomaly to study a gapless phase. As I mentioned that the gapped phase are related to topology, which are easier. The gapless phase is a much more difficult question and maybe represent a future direction. And here I want to say that there is one way to study gapless phase via gapped phase, in particular via this notion of a non-invertible gravitational anomaly. Actually, usually people say that anomaly don't contain too much information. Probably it's not enough to start using that to study gapless phase. But however, here I want to emphasize that this non-invertible gravitational anomaly actually contain a lot of information. So because it contains a lot of information, maybe it's possible to use this information to characterize or maybe even classify a gapless CFT. Okay. And for the convenience later, we'll also we also give this non-invertible gravitational anomaly another name called the categorical symmetry. The categorical symmetry is just another name for non-invertible gravitational anomaly, which is another name for topological order in one higher dimension. So actually, there's one object. We give three names, either topological order in one higher dimension, or non-invertible gravitational anomaly, or categorical symmetry. They all mean the same thing. And here I try to, in the next, we try to present the case. Maybe we can use this categorical symmetry to characterize and classify a gapless conformal field theory. Okay, and So this is really try to build a case for this statement. This may not be accurate, and maybe you need modification, but that's maybe a direction of effort. Okay. To really go into that direction, so let's remind you that remember that a two-dimensional 2+1D topological order is characterized by degenerate ground states, or in more detail by the modular matrix. This is a regenerative representation of a mapping class group of a torus. Okay. So here I want to explain a little more detail how to understand the degenerate ground state from categorical point of view. Okay, so it's convenient to consider space-time, which is a cylinder. So this M3 is a solid cylinder. It's solid cylinder. So here, this face and that face is identified. So this solid cylinder is our space-time. And the real direction is a time evolution direction. So they are Euclidean evolution. So when you have a Euclidean evolution for a long time, it's like a projection to ground state. So therefore, this kind of state-time evolution on the solid cylinder produce a ground state on the surface of a cylinder, which is a torus. Okay, so this is kind of geometrical view to view the degenerate ground state on the torus via this evolution of represented by this solid cylinder in space-time. But however, this pure solid cylinder only gives rise to one ground state. How to get other degenerate ground states? And to get other degenerate ground state, we can insert the word line of a type I anion in the middle of a solid cylinder. Okay, which wrap around this S1 direction. Okay, and again, this time evolution is projection that give you another different ground state because this insertion. So from here you can see that the different degenerate ground states are labeled by the anion type in the bulk, and then this ST matrix also is an index of ST matrix, also is anion type. Okay, and so this ST matrix labeled by anion type really gave this characterization of 2+1D topological order, or equivalently it is a 1+1D non-invertible anomaly, or 1+1D categorical symmetry. So you'll say that what is a 1+1D categorical symmetry? How to label them, how to characterize them. I say, okay, SNT matrix, which is labeled this categorical symmetry. Or this more precisely is a unitary modular tensor category, which is labeled a categorical symmetry in 1+1D. Okay, that's some background. Okay, so now let's try to explain why this 1+1D categorical symmetry can characterize or determine the 1+1D conformal field theory. Or another way to say how this ST matrix can characterize or determine 1+1D conformal field theory. And here I want to say that when you have a 1+1D conformal field theory, and it have a partition function defined on the space-time with some shape. So space-time is like a shared torus. Okay, the shape of space-time is parameterized by this complex number tau. So that kind of moduli space. Okay, and then the partition function actually is a modular invariant, and the modular transformation they are invariant. Okay, so this is true for the partition function in 1+1 lattice model, 1+1D lattice model. So in some sense, we can say that the modular invariant partition function means anomaly free, means realizable as a 1+1D lattice model. So this modular invariance means anomaly free in 1+1D. But however, when you have a 2D topological order and consider it's a gapless boundary, if a boundary of a 2D topological order are described by conformal field theory, then this conformal field theory will be anomalous. Okay, and this anomalous conformal field theory actually have a multiple of a partition function. So it do not have a single partition function. The partition function have many components. Okay, why is that? Because of the following. When you have let's using this a cylinder to represent space-time of a 2D topology order. The 2D topology live on the disk, and the vertical is time direction. Okay, and then this different partition function correspond to insertion of a anion in the middle of the in the middle. But this anion in the middle is far away from boundary. So in some sense, the boundary is still the same. But however, insertion of anion in the bulk change the boundary sector, actually gave us different boundary partition function. Okay. And so therefore, the different boundary partition function, again, labeled by an anion type in the bulk. Okay. And so this multi-component partition function actually very much similar to the degenerate ground states. You know, this graph and this graph is the same. It just rotate. We just rename y as t or rename t as a y. It's just renaming these two labels. In the Euclidean space, you call this t or call it y, doesn't matter. So the degenerate ground state actually correspond to this multi-component partition function, and which in turn that we say that this multi-component partition function is a modular covariant, and this modular covariance is a generalization of a modular invariance, and the modular covariance is characterized by this ST matrix, again characterized by this anomaly or this categorical symmetry. So therefore, using this modular covariant condition, we can determine the boundary partition function. So this is what I mean by using the bulk topology order, or using this non-invertible anomaly, or using this categorical symmetry to determine the boundary conformal field theory. Yeah, it's really using this kind of relation. So let's try to apply that relation in a simpler case. We consider the gapped boundary. The gapped boundary. For the gapped states, the partition function is a constant, do not depend on tau. It's topological, so it's a constant. And but in one dimension, this partition function turns out to be an integer. That has to be integer. Okay. So therefore, to obtain gapped boundary of a 2D topology order, we need to solve this this equation and looking for the integer solution where the first component equal to 1. Okay, there's some normalization condition. Okay, and for the Z2 topology order, this two-dimensional gauge theory, this ST matrix is this 2 4x4 matrix, and then we find two integer solution for this equation. And one is 1 1 0 0 or 1 0 1 0. And the first condition have an E condensation. Let me explain it a little bit. Why it have an E condensation? Because this Z1 equal to 1, they always equal to 1. Means we have the partition function. It just means you have a ground state on the boundary. That's ground state on boundary is just 1. Partition function equal to 1 means you have a ground state with 0 energy. Okay. And however, if you insert an E on the middle, then you say that's impossible. We cannot create an E alone. So we can create a pair of E particle in the bulk. Then moving this bulk E particle to the boundary. If a boundary can absorb this E particle, then we arrive at a situation where we have a single E particle in the bulk. But another E particle is absorbed by the boundary. The boundary can absorb the E particle means E is condensed. So therefore, therefore we have a E appear in the bulk. The boundary is absorbed by a E, absorb another E, and so that's this one. But however, if you create M particle in the middle, you can also create a pair of M particle and moving M particle to the boundary. But this boundary cannot absorb M particle. So M particle appear as an excitation on the boundary, have energy. Then in the long time limit, this final energy gives rise to this zero partition function. So this 0 means that the M particle is not condensed on the boundary. And this 0 here means the F particle is not condensed on the boundary. Only E particle is condensed on the boundary. Similarly, in this case, the M particle is condensed on the boundary, but the E and F particle is not condensed on the boundary. So there's only these two kinds of a boundary for this E2 topological order. Okay. And then using this example, I can explain why we call this anomaly as a categorical symmetry. Why we give another name? You know, you gave something known a new name seems to mean anything, but here giving a new name motivate us to thinking in new directions, and so it may mean something. Okay. So this new name, this categorical symmetry, this name really is motivated by the following thing. The 2 + 20 topological order have a conservation. You know, E particle have a Z2 conservation because this Z2 fusion rule. The M particle also have a Z2 conservation because M particle also have a Z2 fusion rule. So therefore, there's a 2 conservation of in the 2 + 20 Z2 topological order because the 2 fusion rule. Certainly you can say this F particle also have a Z2 fusion rule. That's another symmetry. But actually, because F is a bound state of E and M, so this one is not independent. It only have 2 independent Z2 fusion rule. In physics, when you have a conservation, we say there's a symmetry. So therefore, this 2 + 20 Z2 topological order have a Z2 symmetry coming from a conservation of E, and Z2 symmetry coming from a conservation of M. So I have 2 symmetries. Okay. And however, on the boundary, because the boundary is coming from this E condensed. So that's why we have a spontaneous symmetry breaking. The condensation means a spontaneous symmetry breaking in physics. So therefore, it's like the bulk Z2 symmetry is spontaneously broken to the single Z2 symmetry of M conservation. But the other boundary, we have M condensation. So the other boundary can be viewed as a symmetry breaking of a Z2M. So only Z2E is preserved. So therefore, we can describing these 2 boundaries as a spontaneous symmetry breaking of a categorical symmetry. The boundary, they partially break this 2 Z2. Is the first one or second one. So therefore, calling gravitational anomaly or calling 2D topological order as a categorical symmetry is really motivate us to using this language, using symmetry breaking language to describe the boundary. But however, this 2 symmetry is not a direct product. So I'm using the V symbol to say there's some composition of 2 symmetry. The reason because this E and M particle have non-trivial mutual statistics. If you move E around M, they have a pi. They have pi mutual statistics. So therefore, these 2 symmetries are not independent. If E and M have a trivial mutual statistics, then these 2 symmetries will be independent. We'll say this times Z2 times Z2. Because non-trivial mutual statistics, these 2 symmetries are a little bit special. In particular, because this non-trivial mutual statistics, we cannot break both symmetry together at the same time. We cannot break all of them together. We can only break one of them. Okay. So using this picture, we can say then that's for gap states. Then for the gapless states, using this picture, how to describe the gapless states. So here I want to say that the E condensed boundary and the M condensed boundary, there's 2 gapped boundary. And there's a phase transition between these 2 gapped boundary. And the phase transition is a continuous and it's a critical point. This critical point is a gapless. Okay. So remember this the E condensed boundary is that we break the Z2E symmetry. And the M condensed boundary break Z2M symmetry. But however, at this critical point, we don't have E condensation nor M condensation. So actually, this critical point have a full categorical symmetry, and so this is a point. So therefore, we can view this 1 plus 1D CFT as a gapless space with a full categorical symmetry. Okay. And so this is really what we mean by this categorical symmetry can be used to determine or even classify CFT. Okay. So let's try that to see, is that really true? Can we use categorical symmetry to completely determine the CFT? So as I mentioned that this Z2 topology order or this Torah code model, whose categorical symmetry or 2D topology order are described by these two ST matrix. Okay, these two 4x4 matrix describing 2D topology order or categorical symmetry. Okay. And the gapless boundary would have a 4 component. And now because the gapless boundary, we are looking for the partition function which have tau dependence. And also we're looking for the solution with no condensation, means that we're looking for the solution of this equation where every component is non-zero. So there's no condensation. Every component is 0. It's non-zero. Okay. And actually, we find that the solution of this equation is not unique. There's many solutions. So here is just 1. So both of these 4 component or characters of CFT character are solution of this previous modular covariant equation. The first one is a familiar one. It's called Ising CFT. The second one is a minimum model. This is a 5-4 minimum model CFT. Central charge is 7/10. Central charge here is 1/2. So we see that the correspondence is not 1-to-1. So, but we can improve it because you can see this solution is more special. It has a minimal central charge. The minimal central charge means the minimal number of excitation. So therefore, maybe a categorical symmetry can determine a minimal CFT, which is minimal central charge. And maybe this correspondence is 1-to-1, or close to 1-to-1. May not be exactly 1-to-1, but close to 1-to-1. So we are really trying to push in one direction, but we don't know exact result. But we hope we get something non-trivial here. So so by choosing the minimal central charge, we hope to get a better 1-to-1 correspondence. Okay. So actually, this idea is put in a very general form in terms of topological weak rotation. Okay. So for every topology order, we can have a boundary which the boundary do not have any condensation, and this boundary is gapless. But simply saying the boundary have no condensation do not uniquely determine the boundary, because you can always stack a normally free boundary to the boundary of a bulk. But we can again we can have additional requirement require the minimal amount of boundary excitation. Maybe there's a near 1-to-1 correspondence, and this is described as topological weak rotation. And so maybe one can using the 2D topology order or unitary modular tensor category to classify 1 plus the rational CFTs. And but actually, there's another idea, again using the symmetry. In some sense, the categorical symmetry can be viewed as an emergent symmetry of the Ising model. Okay, so let me come to this point. So we say that the critical point have this categorical symmetry. It means that it have a Z2 symmetry of conservation of E, and this is well known because the CFT of Ising model have Z2 symmetry because Ising model have Z2 symmetry. Their CFT of phase transition also have Z2 symmetry. Okay, but however, this statement really say that the Ising CFT also have emergent symmetry, have this additional Z2 symmetry. This is Z2M symmetry. So in addition to Z2E symmetry, there's another Z2M symmetry in Ising critical point. And these two emergent symmetry is put together in some non-trivial way, which is called the categorical symmetry. So therefore, this categorical symmetry can be viewed as an emergent symmetry, which appears only in low dimension from this CFT. Okay. So so then we can ask what is emergent categorical symmetry of this CFT, this Ising CFT with 4 components. Then obviously, as simple, their emergent categorical symmetry is this Z2 topological order in 2 dimensions. But however, we can ask, do we have an even larger emergent categorical symmetry? You know, in physics, you may have emergent symmetry, but however, you may missing something. Means maybe actual emergent symmetry is bigger than you thought. Okay, certainly. So here we are asking the same question: do we have an even bigger emergent symmetry? So that's a renaming help us to thinking this way. Do we have a bigger emergent symmetry? Another way to say that can we view this Ising CFT as a boundary of a more complicated 2D topological order with more anyons, or more generally, bigger total quantum dimension. Actually, I don't know how to define that in higher category, but at least in modular tensor category, we have this total quantum dimension. I assume something similar can be defined for higher category. So therefore, we want to view the Ising model as a boundary of something more complicated topological order. So they have a bigger categorical symmetry. Actually, the answer is yes. Actually, the Ising model, this Ising model, is a boundary of this, I don't know how to call this. There's a unitary tensor category, also called a unitary modular tensor category, also called Ising, and is a conjugate. And this double Ising have a 9 anyons. So there's a 9 by 9 there's 9 component partition function, and which satisfy this modular covariance. So therefore, the Ising CFT actually have a so-called emergent maximal categorical symmetry, which is given by this double Ising model, a double Ising of a modular tensor category with the 9 anyons. Okay, so so therefore, so this maximum categorical symmetry maybe is more useful. Similarly, remember this another solution of Ising this modular covariance for the Z2 topological order. This is another solution, and this one is this minimum model of 7/10 central charge, and this one actually not only have this Z2 categorical symmetry, it's actually have an even bigger categorical symmetry. Okay, this even bigger categorical symmetry correspond to the 2D topological order of this kind, you know. And the first one is a Fibonacci onion model, Fibonacci model we mentioned. It's also actually the G2 level 1 Chern-Simons theory. The second one is a twisted Ising model. It's an Ising unitary fusion category, but with some twist. And so tensor product of 2. And then the other one is a time reversal conjugate. So this kind of 2D topological order realize have a boundary given by this kind of minimum model CFT. So therefore, this minimum model CFT have a maximum categorical symmetry given by this kind of 2D topological order. So this really very suggestive. Maybe this is a better way to say that 1 plus 1 irrational CFT maybe have a 1-to-1 correspondence with a maximum emergent categorical symmetry. And so we can using the maximum emergent categorical symmetry to classify 1 plus CFT. And here I just want to mention that choosing the maximum emergent CFT is like choosing the smallest character. We're using this single character, this part, rather than some of these several characters. This is a single character as the trivial component of partition function.
And then because the trivial component is chosen to be the minimal character, then the partition function should have a more component to have modular covariance. Okay, basically that's the idea. And this way you get a maximum categorical symmetry. And so this idea may work in higher dimension. And we don't know, but this is really quite a jump. Whether in higher dimensional gapless CFT, one can also define the maximum emergent categorical symmetry. Okay, so here, let's just consider an example. Let's consider a higher dimensional theory, like a 2-dimensional, 3-dimensional lattice model with a G symmetry. G is a finite group. Okay. Then this G symmetry breaking point have a phase transition. You know, this G symmetry breaking transition is described by the critical point. And this critical point should have a G symmetry. Okay. The critical point of a G symmetry break transition should have a G symmetry. Actually, in this paper, we show that it also have another symmetry. It's called the higher symmetry. But this is not really higher symmetry. It's a generalization of a higher symmetry. So we call this an algebraic higher symmetry. So this is some kind of algebraic higher symmetry. It's a generalization of a symmetry and a generalization of a higher symmetry. And this is not described by group because higher symmetry are described by higher group, but this one is not described by higher group. Okay, and so actually this critical point have this kind of a categorical symmetry. And this also works in 1 + 1D. But however, in 1 + 1D, this one is not maximum. But in higher dimension, we don't know, but this one may be maximum. So therefore, this symmetry breaking transition corresponds to this kind of a categorical symmetry. But as I mentioned, that categorical symmetry just means a non-invertible anomaly, or means a topological order in 1 higher dimension. So what is this topological order in 1 higher dimension, which corresponds to this kind of categorical symmetry? The answer is a G-gauge theory. So the topological order described by G-gauge theory is corresponds to this kind of categorical symmetry. Okay, so therefore we see that we have a relation between CFT and this categorical symmetry, means topological order in 1 higher dimension. And this relation is very much like ADS CFT duality. At least this CFT and this CFT is the same. And this ADS seems like a corresponding topological order in 1 higher dimension. So let's try to explore that connection. So what's the relation between categorical symmetry or non-invertible gravitational anomaly and the ADF-CFT duality? Okay. So in the ADF-C duality, we have this following 2 statements. Okay. If at the boundary we have a G symmetry, then that means the ADS bulk would contain a G-gauge theory. That's one statement. Another statement is that if ADS bulk contains a G-gauge theory, then the boundary should contain a G symmetry. Okay, so that is a 2 thing people say in the ADS CFT duality. But however, what we try to say here is that it's something similar, but a little bit more precise, more tighter. You know, it's a tighter statement. And we say that if bulk have only gauge theory, but this gauge theory should allow charge fluctuation and flux fluctuation. So that is a gauge theory which allow charge fluctuation and flux fluctuation, and certain gravity. We always have a gravity in the bulk. So this particular, that's what we call pure gauge theory. If a bulk have this pure gauge theory, then the boundary is this particular critical point. This boundary CFT will be the CFT describing this G symmetry breaking transition CFT. Okay, so the pure gate theory corresponds to this G symmetry breaking CFT, and and also reverse also true, that is this symmetry breaking CFT at the boundary corresponds to pure gate theory in the bulk. Okay, so actually this is what we described. That is so the symmetry breaking transition CFT corresponds to pure gate theory in the bulk. Okay, but so in some sense, this ADF-CFT structure describe how we transition from a boundary to the bulk. So actually there's some layer. Boundary have the neighborhood. This boundary neighborhood probably is like this have this geometry of ADS structure, which is really describing this gaplessness of the boundary. So really come to this picture. So we have a CFT on the boundary, which actually this boundary CFT really characterized by this geometry, this ADS geometry. We'll go to further to the infinity, we get the bulk gap theory, which is a pure gate theory. So this is like a combination of these two pictures. So this is this ADF CFT connection. And so the bottom line is that maybe this a maximum emergent maximum categorical symmetry probably carry a lot of information. Maybe we can use that to classify, to characterize this gapless system. Okay, yeah, that's all. Thank you.
Well, thank you very much. So are there some questions for now? Otherwise, let me recall there will be this discussion session. And I suggest that Xiaogan goes to discussion session #1 as yesterday. So any questions for now?
So maybe I just have a very quick question. So if this G m plus m minus 1, that's not a higher group, right? But
not higher group.
Still some sort of higher symmetry. What is that?
Okay. Yeah. Let me try to see. Okay. And okay. I'm sure you can write something. Okay. Yeah. So so usually when you have a symmetry, you have this U G, and then you multiply another U G prime. You get another transformation is U G and G prime. So that is a group-like symmetry. Even higher symmetry or higher form symmetry have this group-like relation. And but however, for this algebraic higher symmetry, we have algebra. So basically, we have the composition for two symmetry transformation, U and U prime, give us a sum of W plus W prime plus. There's a sum, okay. And so it's more like an algebra. And so actually this kind of symmetry is more like this kind of algebraic.
So it's this EF2 thing. It's like the EF2 case.
Yeah, it's like a fusion category. You know, the ordinary symmetry composed like a pointed fusion category. But actually, that's maybe too much restriction. We could allow symmetry operation which compose as a more general fusion category, which contains sum. Yeah. So so this is called algebraic higher symmetry. Also, there's this kind of thing studied in 1+1 dimension CFT called the non-invertible defect line, because in CFT people study symmetry using defect line and non-inverted defect line in CFT also corresponds to that. So you can also call this a non-invertible symmetry. Or I think also some people call it maybe fusion category symmetry or something. You know, this it's something new, so there are different names. And in this paper, we call this algebraic higher symmetry.
I have a question. What is the precise mathematical definition of the V product in categoric symmetry?
No, there's no precise definition. This is really a physicist invention. It just say that because categoric symmetry is quite different from symmetry, but however, it has parts which are very similar to symmetry. Say like this Z2 topological order, the conservation of Z2 charge is very much like ordinary symmetry, and the conservation of Z2 flux is like a ordinary higher symmetry. But when you combine them together as a Z2 gauge theory as a whole, then it's not quite a symmetry. It's really unitary fusion category or some higher fusion category, but it's a part really like a symmetry. So that's why we invent this name to emphasize it have a parts really like a physics symmetry. But this is really not a precise notation. And the full data is this fusion higher category is the full data to characterize a categorical symmetry.
Excuse me, when G is abelian finite group, isn't that G n-1 is just a higher symmetry?
Exactly. So only when G is not abelian, it became algebraic higher symmetry.
I agree.
But if G is abelian, then everything can be rephrased within this higher form symmetry.
Thank you.
I also have a question. So you mentioned this conjecture that perhaps emergent symmetries in the bulk, they will classify CFTs on the boundary.
Yeah.
So right, part of the CFT data is the spectrum of anomalous dimensions. How would they translate, assuming it works? How would you read anomalous dimensions from your emergent symmetry?
Yeah, this is a very good question. So let me just clear this. Okay. So actually, let's say for this example, and we can see, yeah, from here you can see this relation. So this IJ are these three label of three anion in the Ising unitary fusion category. So this a trivial object, there's a fermion, there's a sigma. So usually this is a trivial, this is a fermion F, this is sigma, this is 1/16, this Ising anion. Okay. So from this relation, you can see that this topological spin of the anion in higher dimension happen to give rise to the fractional part of scaling dimension in the boundary CFT. Okay, so this connection is very direct, but however only the fractional part, the integer part of spin are kind of descendant field coming from derivative, and that part is not really captured. Okay, but the fractional part of scaling dimension is related to the topological spin.
Mm-hmm. Okay.
So there's a very direct relation. Yeah.
Mm-hmm. I suggest we just leave the session open as usual. So if you have more questions, please ask more questions. And otherwise, we meet again at 5:30 European time for the final talk of this session. And Xiaogang, thanks again for this wonderful mini course.
Thank you for organizing this meeting. Really, we see a lot of new faces. These really two different communities coming together. It's very exciting.
Thank you very much.
So I don't know, but well, I don't know the physics, but it seems like isn't that like this algebraic symmetry that you just described? It looks like in our case the EF2 case, emergent fermion 2 case.
Maybe yes. Probably, yeah. It's like a EF2, and it's not pointed anymore. You know, the ordinary symmetry or higher symmetry, they're kind of like pointed. So their fusion always a pointed fusion. And this algebraic one just generalize that into non-pointed composition. And indeed, the EF2 case have also this non-pointed fusion. And it's related to that. And we need to generalize that because you know, this symmetry breaking for non-abelian group is a pretty common appearance in physics. But to really using emergent symmetry to describe that case, we have to generalize this symmetry to algebraic higher symmetry so that you can see this critical point have some kind of emergent algebraic higher symmetry.
Yeah, I guess it's my homework to understand this.
Can I ask some vague question?
Yes, please.
So, so how can I relate your story to the topological defect lines in CFTs? Say in Ising case. So usually in that context, the topological defect line, we consider the Ising CFT with the modular invariant partition function, and we still say that the Ising fusion category acts on the theory. So how can I relate that to your story?
Okay, yeah, and so okay, let me see. I can understand your question here. You can see here that the definition of partition function may be slightly different. So here we define partition function as a boundary of a bulk. So we specify the bulk. If bulk have no excitation, we only have this trivial component of a partition function. So yes. So we only have this part. Yeah. The bulk don't have a anion. We only have this part. But this part is not a modular invariant. And so to make a modular covariant, and we say that we insert an anion in the middle to obtain other component of a partition function, yeah, which actually correspond to the CFT with different defect line insertion. And we don't add them together. We just leave them alone as a different component. Then the whole thing became modular covariant. And this modular covariance actually is this ST matrix happen to correspond to the bulk topological order, what kind of anion you insert. Okay. But however, when you consider the so-called maximum categorical symmetry, we allow us to redefine the boundary sector. Usually the conformal field theory, their sector are specified. Here we say we don't specify sector in order to see even bigger symmetry. That is like in this case. If you want to see this this kind of Z2 categorical symmetry, we have a fourth sector. But we can see the bigger symmetry. We say, okay, let's assume or consider CFT where whose partition function is given by this sector alone. Okay. Then you'll see that their module transformation require more component, and you get a more complicated topological order in one higher dimension. And this we interpret this phenomena as a bigger categorical symmetry. So that's a more emergent symmetry. And so this bigger categorical symmetry maybe carry even more information. So we are hoping maybe this maximum categorical symmetry carry more information, maybe it's closer to a classification. That's basically the idea.
Maybe I might be asking that how can I see the Kramers-Warnier duality from that categorical symmetry Z2 wedge Z2?
Kramers-Warnier duality basically exchange of E and M.
Yes.
It's this symmetry it's actually, I think it's realized in this case. So E and M exchange symmetry is contained in here. So in this case, in these two, the categorical symmetry, this Quantum wire duality is not incorporated. Let me explain what I mean. You can see those symmetry, those 4 components incorporate to Z2 symmetry because Z2 symmetry is a defect line at a boundary condition. That's what gave rise to 4 partition function. But the Kramer wire duality is act externally in this case, just exchanging E and M. So these 4 components do not change. But they do not appear as a defect line. So if you want to incorporate the Kramer wire duality symmetry as a defect line, you generate more component, and that gave rise to this 9-component partition function. So this 9-component partition function, the Z2M symmetry, Z2E symmetry, and the Kramer wire duality symmetry, all included as a defect line, as a boundary condition. So that's how we get a 9 partition function. So this one is included internally. So therefore, actually, that's why we have even bigger categorical symmetry. So therefore, this is a very good question. This maximum categorical symmetry of Ising CFT actually contain Kramer wire duality symmetry.
I feel that somehow the Z2 gauge theory in the box should know the Kramer's wire duality because that Z2 gauge theory have the symmetry exchanging the E and M. And therefore, you actually have a surface effect. So
the
you
Z2 gauge theory in the box don't have EM exchange as a symmetry, as a physical symmetry. Means the Hamiltonian have energy. As a topological theory, it have a symmetry. But as a generic topological order, the M particle, E particle may have a different energy gap. So they don't have that as a physical symmetry.
Yeah, but in the
you need to gauge.
If
you gauge this EM exchange, you get a double Ising model. After you gauge this EM exchange, then you force that to be a symmetry. So actually, that's another way to say that this double Ising model coming from the Z2 gauge theory after you're gauging the EM exchange symmetry. And this is really after gauging, that became categorical symmetry. Before gauging, that means we overlook that symmetry. So because in physics here, when you see topological order, the topological kind of arbitrary Hamiltonian and not ideal Hamiltonian. So all these topological excitation may have different energy gap. So they don't have a symmetry unless you gauge them.
I see.
Xiaogang?
Yeah.
Is the categorical symmetry somehow related to the quantum double?
Yes. So the categorical symmetry is actually categorical symmetry equal to topological order in one higher dimension, equal to unitary modular tensor category, and equal to quantum double in the gauge group sense. Yeah. So therefore, when you have this we have a group, the categorical symmetry is a quantum double of that group.
Mm-hmm.
Yeah. So that is
okay.
so maybe that's a statement that became more simple. That is at least in 1+1 CFT, which have a G symmetry breaking, their categorical symmetry is a G quantum double.
Okay, so may we say that the categorical symmetry is a sort of generalization of the quantum double?
Yes. So the quantum double is like a topological order in one higher dimension. So we can generalize that. So categorical symmetry also topological order in one higher dimension.
Okay.
Yeah. So in that sense, it's generalization. So like a categorical symmetry can be a unitary modular tensor category. So that's generalized quantum double.
So yeah, it's possible to give some formal definition of the categorical symmetry?
It's a topological in one higher dimension or non-invertible graphing anomaly. And then the next thing is how to define topological in one higher dimension, whether there is a more rigorous definition. Yeah, that became a pressing issue.
Yeah, I would like to view these things from the point of view of representation theory or generalization of representation theory.
Oh.
So
that'd be great. I don't know. Yeah.
Obviously, when we say quantum double,
yeah,
is the representation of some half algebra.
That's really great point. And
yeah.
So let me expand on this a little bit. So here we are talking about the categorical symmetry of Z2 gate theory. Or this Z2 quantum double. Okay. And it have two representation, which is given by these two solutions.
Mm-hmm.
That's a gap the boundary is the simplest representation of this quantum double. But I don't know how to view that way. But I imagine there's a representation theory. One can find a representation of quantum double, and I can say this is the answer for that. In some sense, solving this equation is a little bit like looking for representation of the quantum double.
Okay.
Yeah, and the simplest representation is this. However, the more non-trivial one will be this infinite dimensional representation. Those are infinite dimensional representation because the conformal fields are spectrum infinite dimensional. So those are two infinite dimensional representation. And in this case, the different modules are grouped differently. You can say we group these two modules together as a single module. And this may not be necessary. We can look at this as a single module. Then it's a representation of, and view this as a non-trivial module. In this case, we get a bigger categorical symmetry. So actually, this representation can be viewed as representation of some bigger categorical symmetry. And that maybe you get more information. Yeah. So indeed it's this, but I don't know how to formulate that precisely. So that's definitely the direction. So view everything as representation theory. We have representation of a group symmetry, representation of a higher symmetry, and representation of a categorical symmetry, which can directly correspond to CFT. So this correspondence really is a representation of this categorical symmetry equal to CFT. We hope we have something like that. But I think we only have something very partial. That is, we view this deriving representation like solving this kind of a modular covariant equation. But we don't have a better way. And this is really, really important because in 1+ dimension, because partition function have this holomorphic structure, we know how to do this. In higher dimension, we don't have this holomorphic structure. We need something more. We don't know. So that's a bottleneck at the moment. Hopefully, this point of view of representation theory maybe can help us to have some idea. So this idea may even works in a higher dimension. Yeah.
Okay. Yeah.
That is
very good. You have
given
an excellent lecture. Yeah. I enjoyed it very much. Okay.
Can I add a few thoughts?
Yeah.
About the V product we propose, I think it want to give some sense that this say G V product, the Gn minus 1, we want to say something like this G and G minus 1 are some sort of dual to each other. So if we start from, exactly. It's want to reveal there's a duality between these two parts.
Yeah,
so if we only know part of it, say we only know the Gn minus 1, there should be a way or a recipe to find out its dual, then put the two together, we get this whole categorical symmetry.
Exactly. Yeah, this is a very, very good point. So maybe this notation do mean something. They mean a lot. Okay. So this G like a E, like a charge. This is like a magnetic. So this G and a G n minus 1 is like a what do you call this? Magnetic duality, charge and magnetic duality.
Yeah, electromagnetic
duality.
duality.
Electric magnetic duality. Yeah. So if you incorporate the electromagnetic duality, this notation probably became precise. Yeah. So this is this became, and also you can imagine, you can generalize. Maybe this one also is some kind of algebraic higher symmetry. Is electromagnetic duality is some other things. So this notation really means that this categorical symmetry have two parts, which are related by this electromagnetic duality. And then in this sense, this notation may become very precise and useful. Yeah, this is a very good point indeed, Wenjie.
Yeah, when the G is generalized from algebraic symmetry, it's going to describe by some higher fusion category. And usually there's notion of some dualizable fusion higher category. Then we need to find its dual.
Yeah.
And another thing, it's we mentioned that we can get this much for the 1 plus 1D case because the 1 plus 1D series has this holomorphic, anti-holomorphic separation. I think this in 3 plus 1D, there might be possible to generalize as well because there's some, say U1 theory, you can separate and they describe by some gauge field and
I see.
curvatures. They can be separated into self-dual component and anti-self-dual component.
Yeah, there's some kind of, especially that's another thought, a direction. If this holomorphic, anti-holomorphic can be have some higher dimensional generalization. And then we can just use the approach in 1 plus 1D to higher dimension. Yeah.
It's known that there's such a notion in 5 plus 1D.
I see.
In the context of the 2, 0 supersymmetric CFTs.
Yeah, in supersymmetric CFT, maybe there's such thing. So
but I think it's general too that in 5 plus 1D such kind of holomorphic, anti-holomorphic decomposition exists. I don't know of the 4D or 3 plus 1D or other dimension generalization.
That when you have supersymmetry, maybe you can have this holomorphic, anti-holomorphic. So maybe using this idea, one can start in symmetric CFT. Yeah.
May I ask one thing?
Let me stop sharing. Yeah.
Oh.
Okay.
Hi.
Oh, you want to?
Hi.
Okay. Yeah.
Yeah. Can I ask a quick question? So, is there any thought on how to do this with the continuous group? What would be the dual and what in general the structure would kind of look like?
Okay, and I thought about it a little bit, and so here's my thought. And here I identify categorical symmetry as a topological order in one higher dimension.
Yes.
For continuous group, this identification probably should be abandoned. But however, the notion of categorical symmetry may still be useful.
Right.
We just view this as a ND property. I have certain relation or something constraint. But now we don't view this ND CFT as a boundary of N plus 1D CFT.
Mm-hmm.
Because for continuous group, their charge of flux, sorry, the flux is gapless.
Yeah.
But however, we can use it informally in a sense maybe this N plus 1D topological order have certain limit and became, and physical limit which became a gap, like a velocity go to infinity.
Oh,
and then you can use that. But actually, maybe you don't need to use that. So actually, there's another motivation to have this new name, categorical symmetry.
Mm-hmm.
For finite group, it's identical to topological order in one higher dimension. But for continuous group, it may acquire life of its own. Itself is a concept. It's not related to topology in one higher dimension, but it can be used in a similar way.
I see.
So that's what I'm hoping. So I do feel that for continuous group, you can use that in similar way. And but without interpretation as a boundary of a topological order.
I see.
All right. Sorry to interrupt you. So probably it's a good time to launch the next talk. Anton, would you like to share the screen?
Yes, wait a second.
Okay, I now can see your file. Well, so that's the final talk of the session, and that's the final talk of Anton Kapustin's mini course. So Anton, I give you the floor.
Thank you. So today I would like to discuss another application of the same methods, well, similar methods that have been let's see, describing so far, and specifically I want to discuss how to define Hall conductance as a topological invariant of a 2D gap systems, in the sense that it's an invariant of a phase. And for that I need to define what a phase is. But I'll start with the, explaining how to define the Hall conductance, and then it will be, well, later explain in what sense it's an invariant of a phase. So this talk is this lecture is based on a paper with Nikita Sopenko. It's already online, but we were inspired by this earlier work by 4 authors, Bachman, Prass, and others, which applied somewhat similar methods to define a related invariant called Thouless charge pump. So, right. So let's see. So what was the setup? The setup as again lattice systems with U1 symmetry. So now, so Hall conductance should be definable for any gapped system with a U1 symmetry. So Hamiltonian then, as before, is a sum over lattice point, and each term here is a local observable centered at point P.
Sorry for a naive question. So the Hall conductance, don't kind of know, should it be 2-dimensional or?
Yes. Well, for now, our system is arbitrary, but in the beginning, I'll just discuss U1 symmetry in general context.
Okay. Thank you.
And then I'll specialize to 2 dimensions. Many of the constructions can be made, in a general context. So, okay, so here we have this local Hamiltonian, and well, for simplicity, I'll assume, well, the Hamiltonian is finite range, although that's actually, we'll see later, it's not strictly necessary. You can have like just exponential decaying interaction, that's fine too. So the electric charge operator similarly is sum of local terms. And here I'll be a bit more specific in the sense that now I'll assume a strict on-site symmetry, even though again, it's not strictly necessary. So the on-site symmetry means that each of these charge operators, local charge operator, just acts on a particular site. So it belongs to the algebra observables localized on a particular site and exponentiates to, well, has integer eigenvalues. I write it this way. So these are all just, operator QP and HP are perfectly nice observables, but their formal sums are just formal sums. So this H and Q are not really elements in the algebra observables. We'll see later. Well, it's actually, what are they good for? Well, what they are good for is to define things like symmetry. So first of all, what is symmetry? Well, symmetry just means that each local term is invariant under U1 symmetry. It commutes with the total charge. And this is well defined, even though Q is not an observable, because take commutator, only, since HP has a finite range, really only a few terms here are non-zero. So this is well defined. And more generally, if you have some local observable, then you can define its commutator with the charge without any problems. So, well, okay, strictly speaking, it like some care is needed because, okay, so, okay, for a local observable, localized in some finite set, that's certainly well defined. And that's a variation of A under U1 symmetry. So this condition just says that each term is separately U1 invariant. And well, this is a local transformation in the sense that if A is localized on some finite subset, then its variation is also localized on the same subset. Okay, so well, of course, the most important point about gapped system with U1 symmetry is that there can be no spontaneous symmetry breaking in the situation. That's the Goldstone theorem. Now, so in other words, contrary, that is, if you assume that the system is gapped and U1 invariant, then the ground state is automatically U1 invariant too. Usually it's stated in the opposite direction, saying that, well, if you have a broken U1 symmetry, then you must have gapless modes. Here we just exactly the opposite. It's equivalent state. So now, therefore, we should be able to prove that for any local observable, the average of its variation is 0. So, well, strictly, well, that's actually the precise meaning of the statement that there's no spontaneous symmetry breaking. See, the charge operator is not a bounded operator, so what you get if you act with the charge operator on the vacuum is not clear, it's not well defined typically. But this statement is pretty well defined. Well, actually, some care is needed here too, because see, this variation, this commutator defines an unbounded derivation of the algebra observables. Meaning, well, it's unbounded, so it's actually not defined on the whole algebra A. It's defined on some dense subset. So derivation just means this. So this property. So, but anyway, you cannot define it for all elements of the algebra, but you can define it in some dense subset. Actually, there's a very nice dense subset where it can be defined. So namely, I call it almost local observables. Some subalgebra of A plays an important role in what follows. And the way it's defined is that, well, you say that an element of the algebra is inside this subalgebra if it can be approximated by local observables with very good accuracy. That is, you can always find some ball. If you take a ball of radius r, you can find an observable which is local and localized in this ball, so that it's a very close in norm to A. So equivalently, by the way, so one can also say it differently. One can say that if the commutator of this A with some strictly local observable far from it is exponentially small, like super polynomially small in the radius, then it's almost local. This is the equivalent state. So these almost local observables are just as good as local, but they're more flexible. And for these observables, since they're very well localized, this commutator here is well defined. So this derivation is unbounded derivation is well defined in the subalgebra. And moreover, it's easy to see that it actually maps the subalgebra to itself. Okay, so strictly speaking, we want to prove this for this dense subalgebra, because that's where this delta Q is defined. And that implies then, if you exponentiate this Q to an actual U1 symmetry transformation, it'll imply that expectation value of the U1 transform of any almost local observable is unchanged, well, is the same as before transformation, that is U1 invariance. And that then extends to the whole algebra, because, while infinitesimal U1 transformation, given by this derivation, are only well defined in this dense subalgebra, the actual finite U1 transformation is defined, of course, on the whole algebra A. So, so how do we know that this is true? So this is just this follow from our assumptions. So you might wonder why I proved this Goldstone theorem, but you see the method of proof will actually suggest some important constructions. So actually, I think this proof is probably the simplest proof of Goldstone theorem. Basically, one line, if you know what you're doing. So the point is that one can find. So it's not true. Okay, even though roughly speaking, the whole charge and now it's the vacuum. But as we already discussed, the total charge is not really a well-defined operator on Hilbert's. It doesn't make sense of that. Now, on the other hand, if you look at the Janet's representation of an individual term like that, of course, separately they do not annihilate the vacuum. However, one can find improved observables, I call them Q tilde, such that they do annihilate the vacuum, and such that this new observable is new charge, improved charge on the side P is actually the same as the old one up to this kind of term. So formally, if you sum over all P, this extra term drops out. So in that sense, Q tilde P is as good as QP, because after sum of all the sides, there's no difference between them. And here, this K is antisymmetric in Q and P, some operator, depending on pair of points, which is Q symmetric. So this improvement somehow doesn't change the total charge, but it gives you short charge which annihilates a vacuum point by point wise. So in our language of our previous lecture, K is a one chain, operator valued one chain. And so I like to write this way, using this boundary operator on chains. While Q and Q tilde are zero chains. So it's saying we can correct the zero chain Q by adding some exact term to make this condition true. Okay, suppose we manage to do that. Suppose we know that such an improvement exists. I'll show later why, how to construct such an improvement. But then the Goldstone theorem is proved very easily as well. By the way, so okay, it should be more specific. When I say I have some chains, well, I'm going to use chains valued in not the whole algebra, but in this subalgebra of almost local operators, so that the various combinators are well defined. Anyway, so I want to improve such that this K actually lives in this subalgebra. So anyway, so by the way, so once you're talking about this language of chains and cochains, well, if you have some chain like this, for example, like this, you can contract it with some characteristic zero cochain of X, that is just the characteristic function of a subset. And if X is a finite subset, that gives you a well-defined operator. And similarly for Q. So, and if you ask what's the relation between this input charge on subset X and the old one, well, they differ simply by, well, if you do the integration by parts, you'll see that they differ by something which lives on the boundary of X. So contraction of K with this delta f of X is somehow concentrates everything on the boundary of X. So the improved charge differ only by terms which are concentrated, operators which are concentrated on the boundary of the subset X. And that's the key point. So the point is, first of all, that when you evaluate this commutator of your charge with some local, some almost observable, well, by definition, it's a limit of these commutators as you take ever increasing sets X. But by assumption, well, first, if you plug in what is X differs from, maybe some minus n, and from Q tilde X by this boundary terms. Q tilde X point-wise annihilates the vacuum. So when you sandwich between the vacuum states, the commutator of Q tilde X with anything has zero average. So you're left only with second term. But the second term is right on the boundary of the subset. So this commutator, even before taking the average, is very small when X is large. So if you take X to infinity, this just becomes zero, even before taking the average. So so that's the Goldstone theorem. So it's clear from, well, so this of course is much more structure than the Goldstone theorem requires, but it's actually a very important fact that you can improve your charge by adding this exact operator valued chain to it. So similar manipulations occur in the proof of many different results. For example, similar things can be done for the Hamiltonian itself. Like if your typical Hamiltonian, which is sum of local terms, well, it supposedly annihilates the vacuum in whatever sense. In some sense, again, it's unbounded, it's a bit tricky to define this. But each term separately doesn't annihilate the vacuum. However, one can improve the Hamiltonian in a similar way to rewrite it as the sum of different terms, each of which does annihilate the vacuum. In that sense, every Hamiltonian can be rewritten as a frustration-free Hamiltonian. Every single Hamiltonian, piece of the Hamiltonian annihilates the vacuum. So similar manipulations. So that's like, by the way, it's a well-known result. And I don't know where this proof is probably somewhere in the literature, even though something similar should be in the literature. But anyway, the point. So anyway, so how do we want to construct this one chain? Well, let me, another useful construction is how to think about currents on the lattice. So this essentially appears in this appendix D or C of Kitaev's honeycomb model paper. In the case of, I think, energy current, but similar things that works for electric current. So let's do the electric currents for our purposes more useful. What's a current? Well, again, current is by definition is something which makes this equation true. So the derivative of a charge at some site is equal to sum over over currents from all other points to the site P. It's more like that. So in principle, any solution of this equation, so this one, or this one is a possible current. Now, it is an obvious way to solve this, of course. Here it is. So you can easily check that it just tautologically solves this equation. And by assumption, my assumption is I want J to be skew symmetric because it makes, I want the current from Q to P to be minus the current from P to Q. So this is a canonical solution. It's sort of canonical, but you can ask, okay, wait a second, to what extent is it canonical? If any solution works, how many solutions do I actually have?
Sorry, Anton, I'm not quite sure how do you skew symmetrize it. If you took just one of the terms, that would certainly be a solution to your equation, but what about this second term?
Well, the point is after sum over Q, so my total charge commute, which is each local term. So that's what I can add for free. So it's a U1 variance of the Hamiltonian, which makes it work.
Okay, thank you.
Right, so I added, but it's actually important to make it skew symmetric because then it becomes this chain. So you can ask, well, plus it physically makes more sense, so to have a skew symmetry. Now you can ask, well, how does one parameterize the general ambiguity? Well, there's some sort of obvious ambiguity. You can, of course, add some. You can add something exact, some boundary of some 2 chain with values and almost local operators. You might wonder whether you can add something more elaborate, because after all, you need something close, you can add something which is close to this, and it's going to work. So I'm saying basically that everything close is actually exact. Is it really true? Well, you need to show that this is false, because there's no homology in degree 1. So that statement is actually slightly dimension dependent. And listen, further subtlety. It's really not the homology with constant coefficients I need here, but homology with local coefficients. Local in the sense that I have the current flowing from P to Q. I want that operator to be localized somewhere around P and Q. I don't want it to be localized God knows where. Right? So it's a local coefficient statement I need here. So now this is like getting a bit hairy because, well, this is homology, chain complex. And what I'm supposed to do here, well, it's some sort of a, I guess, it's a simplicial chain complex of some sort. And like what local coefficients usually done for cohomology, not homology. Some sort of funny thing is going on here. I'm not going to get into this. I think it's actually still a true statement. That homology is 0. Well, there's some further subtlety. If you're dealing with dimension 1 system, then homology with non-constant coefficients, like with constant coefficients, actually non-trivial. As I mentioned, the homology with constant coefficients is non-vanishing when the dimension is equal to the degree. So in dimension 1, actually, there is a non-trivial homology. Like, what's going on there? Well, there's a further natural requirement which you want to impose on any sensible current. Namely, suppose you're at infinite temperature, which makes sense in lattice systems. You probably want to say that the current, expectation value of a current is 0. So that's usually assumed because nothing flows anywhere at infinite temperature. Now, so you can normalize, if you normalize our currents always like that, then even in dimension 1, there'll be no like homology, no interesting homology. The statement that there are no currents in equilibrium is actually usually stated as a theorem, something called Bloch's theorem, due to Felix Bloch. And here we see that actually in 1 dimension, you sort of have to force it upon yourself. It's nothing. It's a natural condition In higher dimensions, it's just, it's something you don't assume. It just it's there for free in some sense. But in dimension 1, you have to sort of enforce it. It's a natural physical requirement. Anyway, so when you find the current, what does it do with this Goldstone theorem? Well, it actually turns out that you can construct improvement term for the charge from the current, from any current, doesn't matter which current. You can construct it this way. We can just say, well, there's some solution to this equation. If there's any solution, it's good enough for me. So, so what is the so what is the construction? Well, here's another key ingredient, something called quasi-adiabatic continuation. I'll just call it quasi-adiabatic map because nothing is continuing here. So, described in this paper by Hastings. So, so what is this thing? Well, there is the following. So you can you want to define a map from an algebra to itself, from the algebra world to itself in the following way. You take some element of the algebra, evolve it a little bit in time, and then smear over all times with some function which decays rapidly in time. Now, so this, if the function decays rapidly in time like this, then and if the Hamiltonian is short range, then it stands to reason then that this operator, new operator, is going to be still, if A was localized very well, then this guy is also going to be localized well. The point is that evolution for a finite time just smears out the operator a little bit. Well, if you evolve for a long time, then of course it's going to spread out over the whole system, but then this function is suppressing you there anyway. So the operator, this transformation from A to this guy maps one of a very well localized operator to another very well localized operator. And what else do we want from this function? Well, we also want some condition on its Fourier transform. We want its Fourier transform to be very simple, like this, when omega is large enough, specifically above some delta, which itself is below the gap of the Hamiltonian. So this map is called quasi-adiabatic continuation. Actually, it maps not just A to A, it maps almost local observables to almost local observables. So it's a very nice map. And roughly speaking, what it does, it's like multiplying your operator by like 1 over Hamiltonian projected to the.
Yeah, Anton, kind of right. You probably is it a different slide now? Because
froze. Okay, let's see. I think I should restart sharing.
Maybe maybe you stop sharing and then start sharing again.
Stop sharing, then start sharing again. That happens sometimes. Yeah.
Yeah. Oh, okay. So right. So we haven't seen this slide yet. Just to tell.
So I want to define some map. This map is written due to Hastings, which roughly speaking is like it multiplies the operator, but something like 1 over the Hamiltonian. So in Fourier space, so you would want to multiply by 1 over the frequency, something like that. So so this map is in fact as follows. So it only works for gap systems. So there is the following. First, you fix some number delta, which is between 0 and the gap of the Hamiltonian. Then you pick some function, doesn't matter which one, so this has the following conditions. So it's actually odd function. Sorry, I forgot to say it's a continuous odd function. And it decays very rapidly for large values of the argument. And its Fourier transform is required to satisfy this for large enough frequencies. Large enough meaning bigger than delta. Other than that is arbitrary function. And then you smear your observable, you evolve your observable for time t. This is just evolution operator here. And then you smear it in t using this function. Okay. So roughly speaking, what this does is basically multiplies your operator by like 1 over the Hamiltonians, roughly speaking. And that's not doesn't make sense, but it does make sense if you sort of project out the contribution of the ground state, because on the rest of this Hilbert space. This A is invertible. The Hamiltonian is invertible. The point is you can actually do it on the level of C-star algebra. You don't have to go to Hilbert space. You can actually do it on the level of C-star algebra with another local observable. So, and easy check is that if you just let use a computer, you can just let this K, this improvement current, improvement one chain to be just this transform applied to the usual current, to the electric current one chain. And you can verify that this satisfies all the requirements. So this trick also works for Hamiltonians, as I already mentioned. You can improve your Hamiltonian so that each local term in the Hamiltonian annihilates your ground state. And in that case, you just use not the electric current, but energy current. That I think is actually discussed in Kitaev's appendix, Kitaev's paper on the honeycomb model. Okay, now I finally, with this preparation, when I'm finally ready to define the Hall conductance. So the point is that although the original charges on different sides commute, even on the same, well, they always commute. Now, the one defect is that these improved charges do not commute in general. Nobody said that they will. Nevertheless, since they differ from the original Q only by exact term, then you would expect that the commutator is something exact. And that it's true. The commutator of this chain of these Qs on different sides actually exact in this sense. There's some two chain, operator valid two chain, such that we solve this equation. By the way, there's something interesting going on here algebraically, because we start with this zero chains, and now we defined one chain like this. So what is this thing? So, well, there's some bracket on zero chains, which gives you one chains. It has degree 1, and it's something similar to Gersten-Haber bracket. It has some similar properties. So it can actually be extended to arbitrary chains. So you have some bracket of degree +1, and take into account that if you use homological grading, if you reversed it, you would get a bracket of degree -1, just like in Gersten-Haber case. So I'm not quite sure what to make of this, but anyway, so this is bracket, and we're using it here, just for zero chain. Anyway, so it turns out indeed that's true, and you can actually write explicitly the solution for this operator two-chain M. Easily check that if you just set it to be this, then it solves this equation. And by the way, this commutator here is again example of this bracket. You start with, it's a bracket of now a zero chain and a one chain, and you get to take its bracket in the Gersten-Haber sense, and you get now a two chain. Okay, so, but anyway, just a computation. You can just we need to use fancy words here. So, so we have this now two chain, which measures to what extent this new charges do not commute. And then let's define as a numerical invariant as follows. We just take this two chain and do the following thing. We just pick some point on our plane, divide the plane into 3 sectors, and do what I sort of already sketched a lot last week. We just sum over points P, Q, and R, so that P is always in A, Q in B, and R in C, counterclockwise. And then take the average expectation value in the vacuum. So this sort of sum defines some local observables localized somewhere around here. Because you see, when P, Q, and R are far from each other, this thing decays rapidly. So in reality, if you want P always to be here and Q here and R there, then all these 3 points should be pretty close to each other. Otherwise, you'll get some appreciable contribution from this guy. So in reality, it's all localized somewhere in some neighborhood of this point. So it's a well-defined sum, even though it's infinite sum. Again, using the fact here that this chain is, even though it's not what's called it's not a coarse chain, but it's co-controlled summable. So in other words, you can write it as a contraction of this chain valued, of this real chain, we contract evaluating expectation value of operator value chain M with generator of this degree 2 cohomology of the lattice. Okay, so there's some bad notation here. I used brackets both. In the previous lecture, I used brackets to denote contraction of a chain and a cochain, and in this lecture, I have lots of expectation values. I also use these brackets. So from now on, I'm going to use round, I'm going to use parentheses to denote contraction of a chain and a cochain. Well, brackets will still, well, angle brackets will still stand the expectation value. So anyway, so that's give some numerical invariant in a sense. And the collector that this is up to a factor of 2 pi, the whole conductance. So let me, before explaining sketching the argument, let me explain some properties of this whole conductance. Well, first of all, one kind of very thing to show is that this is actually independent, or this number is independent of the choice of the point and its paths. And that's simply because, see, okay, M, so M satisfies this equation. So it was not closed, but its expectation value actually is closed. Why is that? Because see, each Q tilde annihilates the vacuum. So if I sandwich this in the vacuum state, so this left-hand side will vanish, so the right-hand side will also vanish. So the expectation values are do form a closed two-chain. Right, so it's set here. So therefore, if I can shift alpha by some closed cochain, then the contraction will not change simply by the Stokes theorem. So it's evaluation of a cycle on a cocycle. So it depends only on the cohomology class, which is good because you can easily see that deforming these paths or a point moving in some places just adding some all generators, they'll look like that. So and they'll generate the same cohomology class. So you can move this point anywhere, move this path pretty much anywhere too. You just have to stay away from each other. They shouldn't like approach each other. But if they stay in like their separate sectors, everything is fine. Okay. Now another thing is that this number depends only on the state and the charge, but not on the Hamiltonian. This is much less obvious because to construct this number, I use this chain, and the definition, well, involved solving this equation. The definition, but you need to know what Q tilde is. And my explicit form for M involves K. So Q tilde, definition of Q tilde depends on this choice of this chain K. And K seems to depend on the Hamiltonian. I had some explicit solution for it. And this M also depends on K. So it seems like you do need to know the Hamiltonian to say all this. Well, you need to know that there is some Hamiltonian whose ground state is our state. But turns out you don't need to know the exact Hamiltonian. So the point is that, well, basically we want to fix K simply by requiring this. This has a Q tilde annihilates the ground state. That is, it's connected correlator with any A0. So if turns out that you don't need any specific solution, any solution will do. And one can show that solutions are unique up to this kind of ambiguity. So of course, you cannot add anything exact, but that easily shown doesn't affect anything because we're contracting the cycles anyway in the end. You can also add something which is not exact, but which annihilates the vacuum. And you can show that it also doesn't matter. And turns out that this is actually the only ambiguity. That's some trivial statement, which is not true for, it's true precisely for, you can show it's true for ground states of gapped Hamiltonians. So the only thing we need to use is to show that this is the only ambiguity. And that does use the fact that our ground state is actually a ground state of a local Hamiltonian. To show that, again, you need to use this quasi-diabatic continuation operation. but nothing else. So existence of Hamiltonian is important, but its form is not important. So that's actually a special case of more general statement. You can find the paper, and it shows that ground states of gap local Hamiltonians are quite special. So I don't really know how to describe them among all possible clustering states. So they have very nice properties, but this is property which I'm using, not the specific Hamiltonian. Now I'm afraid my battery is running out, so let me for now let me bring the charger. Sorry.
Okay. Well, we don't need his battery.
So
Okay.
I think I'm back.
So we tried the battery.
Yes. Founder. So sharing. Okay.
Okay, good. We do see your screen.
Sorry, you can see. Okay, great. Okay, so now, so we have this the numerical invariant of any gapped state, which well, should be something familiar, and turns out to be just 2 pi times the Hall conductance. Well, that's not very well. To see that, you need first to massage various, well, there are various formulas for the Hall conductance in the interacting case. So the most general formula people usually write down is the Kubo formula. And this formula has been massaged in sort of a better form in this paper with Les Podineko, wrote a year ago. So one can write it in a way which is better than normal ways. And so in terms of the expectation value of the contraction of the usual current, not this improved one, usual electric current with some cochains, namely, the Hall conductance measures the current in state obtained by applying some electric field. So you start with electric field, which crank it up from 0 to some constant value, and observe the current flowing in the perpendicular direction. So the way you model this, you start with some potential, and use potential specified on lattice, just some function from lattice sides to real numbers. And in this case, well, it actually turns out to be more convenient to take the non-uniform potential. It's not linear. It's just some potential which starts from 0 at, say, like down here, and becomes 1 up there. So create electric field which goes this way. And then you're asking, what is the current, electric current created in this direction? And well, what does it mean? Well, I have to choose some line like that and to compute current across this line. And that's expressed by contracting the usual current with the differential, well, with the co-boundary of another function. So one of the function is just a step function in this direction, this f. And then the other function, which a priori plays a different role, is parameterizes how your potential varies from down here to up there. So in the end, turns out it doesn't matter. This physically they're quite distinct, but the formula to get is very symmetric in these two functions. And in fact, you can take these two functions to be anything, provided they interpolate between 0 and 1. So this magic happens because at 0 temperature, Hall conductance and Hall conductivity, they are the same thing. That is, it doesn't matter how your electric field actually varies. You get the same number. Conductivity is something that you get as a limit of conductance. You need to specify some linear potential, take the range to be very large. But at 0 temperature, it doesn't matter. So in the end, it turns out that you have a very symmetric and nice formula, which involves the currents, these two functions, and this Green's function which I used before. So that's not quite what we want still, because it involves these currents which themselves depend on the Hamiltonian. These are the dynamical quantities. But with some work, we can rewrite it in an even better form, like this. So here, just contract this currents k used for improvement with the same functions, and take the commutator, and then take expectation value. So this formula, by the way, kind of interesting formula because in the previous, so this is just the usual correlator, no like Green's function or anything, just usual static correlator. It's a static correlator. So usually think about Hall conductance something dynamical. You apply electric field, create some non-equilibrium steady state, and then some current flows in some weird direction. So that's a dynamical, it's non-equilibrium statement. And that's why I have all this Green's function squared in this formula, in the usual Kubo formula. But you can massage into a form when there's nothing like that, just a static linear response, basically, or some correlation function, some local observables in the ground state. Such formulas are known in the literature too. There's something called strata formula for the Hall conductance, which is not usually very rigorous. So you can think of this as a version of this, a rigorous version of the strata formula. So anyway, once you reach this stage, you can already see that there is connection with this formula for previous formula for sigma. This also involves this various currents k, and you can massage it further to that form. Okay, so so let me just say what other properties of sigma is. So I already said that it's a numerical invariant of a system, but actually it's a numerical invariant of a phase. The further properties, namely, it turns out to be integral for short-range entangled phases. There's some argument similar to Laughlin's argument, which show that it's integral, but it's rigorous. And moreover, it's an even integer for bosonic phases. And that's something which field theory predicts, which is stated in the very first lecture. Chern-Simon's theory description of quantum Hall effect predicts this, but it's hard to make this precise. So there's something with spin structure. here we can prove it just directly without any, well, by studying statistics of flux insertions. That's another way to argue this. So turns out that this Hall conductance for general systems controls statistics of flux insertion in some very precise way. So in particular, for short-range tangle phases, the only options are bosons and fermions because there are no anyons. And because of that, sigma has to be integral. That's one way to see why it's integral. But more for bosonic systems, you cannot have like emergent fermion in the short-range tangle bosonic system. So you'd expect, therefore, that there's a further constraint that sigma is actually an even integer, and that turns out to be true. So that's how its argument goes. But I'm not going to, this pretty long argument, so I'm going to get into this. You can look at the paper. But rather want to focus on this statement that it's a numerical invariant of a phase, because that gives me an opportunity to explain what I think is the right definition of what quantum phase of matter is. It's an important general issue. So the idea here, well, it's an idea been around for a while, and it's been expounded in this book, Quantum Information Meets Quantum Matter, in some detail. So the idea is that you should really focus on states, not on the Hamiltonians. So that's the first key point. And so when you, instead of, you should define a quantum phase of matter as an equivalence class of gapped states or clustering states under some equivalence relation. So what is this relation? So there are two kinds of equivalences you want to enforce. The more trivial is that if you stack some state with a trivial, that is factorized state, where there's no correlations at all, that gives an equivalent state. That's kind of obvious requirement. Stacking with some completely boring system doesn't give you anything new. It should be the same thing. But the more important equivalence is this one, called equivalence under local unitary quantum circuits of finite depth. So what are these? Well, imagine you have some chain, say, drawing two one-dimensional pictures, even though it's can be done in higher dimensions. You have some one-dimensional system, and the spins sitting on each side. Okay, so there's some state. What can I do with the state? Well, I can apply quantum gates to it, but my gates are going to have a constraint. My gates are going to have a finite, well, each gate is going to be applied to a finite number of spins. So let's say here it's applied to 2 spins, here it's to 3 spins, here it's again to 2. So the size of the gate can be like more than, like, it can be larger, but it should be like fixed by some number. It can't be like go to infinity. And also you do it for a finite number of times. So each layer here is made of some infinite number of gates, and I do several layers, but they only keep number of layers finite. So that's what finite depth refers to. In this case, it's depth 3 circuit. And what is the next each gate? Well, each gate is simply a unitary transformation. So that's why it's called the local unitary quantum circuit. So you apply such local unitary quantum circuit to a state and say, well, whatever you get is equivalent to the original state. It's in the same phase. Now, the good thing, of course, is that, well, in finite system, all states are going to be equivalent because you can just connect any two states in this way, clearly, because you only have a finite number of spins to work with. In fact, you can take one big gate whose size is of order of the system and then just do everything in one step. Of course, well, if you say, well, my size of the gate shouldn't grow with the size, well, that's will make life harder, but you can just do this thing many, many times. You have a finite system, in the end, in a finite time, you're going to connect any two states. That's actually a good thing, because we want this equivalence relation to become non-trivial only in infinite volume. So that's how I think one often talks about phases in the language of states. These equivalence classes under such circuits and under stacking. Now, this definition is not like very physical. It's more like quantum information theoretic and also very difficult to connect with the physics. So here's another one, which is similar. Here you replace a finite depth local unitary quantum circuit with a path in the space of local Hamiltonians. Suppose you want to say that two states are equivalent. When are they equivalent? Well, suppose I have two states called like this, average 1, average 0. If I can find a path of Hamiltonians which are gapped for all values of the parameters of the parameter, such that initial ground states of h of 0 is this guy, and the final ground state of h of 1 is this guy, then I say that the two states are equivalent. The homotopic definition. Now this can actually be phrased in a different way, which is better for purposes. So suppose, well, let's put some additional natural constraint. Well, suppose we have a family of state. Okay, so suppose we found such a path, and suppose as a result, expectation value of all almost local observables are smooth function of this parameter. It seems like a reasonable assumption. Then there is a path of automorphisms which connects these states. That is, there's a way there's some automorphism such that if you apply automorphism and then average over the state 0, that is the same as averaging of the state for some value of lambda. So this continuous path of automorphisms. And moreover, these automorphisms are very nice. They're local in some sense. In what sense? Well, they're basically exponents, p exponents of local Hamiltonians. I call here this unphysical Hamiltonian G of lambda. It's some time-dependent or lambda-dependent Hamiltonian. What I mean by, well, a better way to say it, well, physically, we would just say something like this: that this automorphism is generated by this p exponent. Mathematically, we would say that expectation value satisfies this equation. So it's basically a Schrodinger equation with this unphysical, well, it's some random Hamiltonian G. The important thing about it is it's actually local. It's nice. It's a sum of local terms. It's a zero chain, and each term in this chain is an almost local observable. It's a very nice. It's a nice local Hamiltonian. Well, given this theorem, well, let's call such an automorphism locally generated. That is, local generated if it comes from a local Hamiltonian. That is, it can be written as this, or if you wish, it's an automorphism obtained by solving equations like that. So you can write it in terms of automorphisms rather than in terms of the equation for observables. So therefore, so by the way, so now another kind of trivial observation. If you start with a ground state, which is a ground state of a gapped Hamiltonian, then evolving this using this locally generated automorphisms gives you another ground state of some other gapped Hamiltonian. All that happens, because you see what all that happens, well, it's just basically the fact that it's something known as Lieb-Robinson bounds, that if evolving by a local Hamiltonian takes local observables to local observables. So your original state was a ground state of some local Hamiltonian. And after you evolve it using this automorphism, it's still a ground state of some other local Hamiltonian, which is obtained by just applying this automorphism to every single term in the Hamiltonian. And moreover, you can show that the result is gapped. It's kind of just because of automorphism property, the original guy was gapped, the new Hamiltonian is also gapped. So this suggests like to dispense with Hamiltonians altogether. Just say that it takes the definition. You say that the two states are equivalent if there is some locally generated automorphism which connects these two states. So this is similar to actually to the original definition using local unitary quantum circuits. Essentially, this automorphism is kind of a fuzzy analog of finite depth local unitary quantum circuit. So local unitary finite depth quantum circuit mixes degrees of freedom a little bit, but it maps observable in some site with observable spread out around such site by some small amount, by some finite amount. Similarly, if you apply such this local generated automorphism, then Lieb-Robinson bounds tell you that it's going to smear every observable, well, in principle over the whole system, but the tails are going to be exponentially suppressed or superpolynomially suppressed. So it's a similar thing, but it's much better physically motivated and it's more convenient. So one thing which is follows immediately from this definition is it allows you to glue. It allows you it ensures the following very obvious kind of natural property. If you have two states in the same phase, they should be able to create a gapped interface between them. So that's a very desirable property, and it's kind of difficult to ensure if you're thinking about your states as ground states of some physical gapped Hamiltonians. But if you think of them as just ground states of some Hamiltonians, whose exact form you don't really care for, then it's very easy to glue it. So to glue these ground states. So namely, so suppose you have these two states, I call them phi and phi prime. Suppose they're in the same phase, so that is you can obtain this guy on the whole plane from this guy on the whole plane by evolving for a finite time with some local Hamiltonian. Well, so let's this Hamiltonian be G. So I glue as follows then. I just modify this G by multiplying each term by a step function in x in this say in x direction. So in other words, when x is bigger than 0, then my Hamiltonian is the same as before. When it's less than 0, then it's just 0. So it's kind of seems like some strange operation, but what it does, if you're far to the right, if you're all the way out here, well, that evolution actually doesn't differ from the old one, because what happens to the left of that point, far from it doesn't matter because of this locality. So out here, the new state is going to be exactly like phi prime was. Out here, it will be unchanged. It will say phi. In between, it will be something horrible. I don't know what it is. But the point is, whatever it is, the whole thing is still gapped. Why is it gapped? Well, because it's just evolution of the original gapped state, this one, by this funny Hamiltonian, which is 0 to the left of some line and something else to the right of someone. It has already argued evolving anything with in this way maps a ground state of any Hamiltonian to ground states of some other gapped Hamiltonian. So just this that makes things work. So that's why we can. I propose to define a quantum phase of matter as an equivalence class generated by the following two equivalences. Well, by locally generated automorphisms and stacking with factorized systems. And then I would define trivial phase as the equivalence class of a factorized state. And then following Kitaev, you would say the state is short-range entangled if it's invertible in the following sense, that if you for a state, you can find some other state and another algebra, such that if you stack with it, then you get something in a trivial phase, then you say that the original guy was short-range entangled. So this psi is called the inverse of phi. So you can stack with something else to get something trivial in a trivial phase. And now I can actually explain why I say that this Hall conductance is a numerical invariant of a phase, not just of the system. It becomes completely trivial. The point is that on one hand, I know that I can draw this picture on any part of the plane and get the same numerical invariant for any gapped system. On the other hand, I can glue my phi and phi prime. And if I draw and get some new gapped state in the same phase, well, if I measure Hall conductance out here, I'm going to get, of course, whatever Hall conductance for phi, because the system doesn't even know that something different happens to the right. If you measure it here, I'm going to get Hall conductance for phi prime. But on the other hand, I know that there's nothing should depend on how I choose this graph on the plane, because the whole thing is gapped still. So therefore, they must be equal. So, and this shows that a system with non-trivial Hall conductance, non-zero Hall conductance, cannot have a gapped edge, because it cannot have a gapped interface of the trivial phase. If it had, then we would run into contradiction. So let me just finish by saying what our methods can and cannot do at the moment. So what we do not know how to address is, in fact, a more basic numerical invariant of two-dimensional gapped systems, known as the thermal Hall conductance. So, or equivalently chiral central charge of the edge. So there's a formula, there's a Kubo formula for this, but we don't know how to massage it to any form which would show that it's invariant of a phase in our sense. The trouble with thermal Hall conductance is, strictly speaking, defined at positive temperature. Everything I described only works at 0 temperature, so I don't know how to what to do with thermal Hall conductance. Maybe not even possible using our methods. On the other hand, our methods can be used to rewrite these WZW classes, which I defined before, using states alone. That's work in progress. So before in the lecture 2, I showed how to write them in terms of Hamiltonian and how to write these closed forms in the parameter space. But actually, it wasn't very clear why it should be independent of the state. But once you can do this, it's possible to write in terms of the states, and some interesting algebraic structure emerges. Where this bracket, this Gersten-Haber-like bracket plays an important role. And one can use the same methods to argue that these WZW classes are quantized for short-range entangled system, at least for spherical cycles. I don't know about general ones, but on spheres, integral of WZW classes actually are quantized. And there's some recursive argument which connects these WZW classes to the integrals of usual Berry curvature. And so the point being that, somehow they're all descendants of the Berry curvature. So once you know that Berry curvature is quantized, you can deduce on spheres, you can deduce that these WZW classes are also quantized on spheres. A very important check would be to see whether these WZW classes are quantized not just on spheres, but on arbitrary manifolds, for arbitrary families. That's what field theory predicts. And that would be a strong argument that, supporting argument that evidence that field theory actually is relevant. Because in field theory, you can put your system on any manifold, but for our lattice systems, cannot be put on any manifold. So all we have is topology in the parameter space. Quantization of WZW classes on some non-trivial manifold, not spheres, would be an important check. All this conjecture that relates short-range entangled phases to field theory. Okay, so I think I'll stop here.
Well, thanks a lot for this nice mini course. We conclude this main session and we pass to discussion sessions. I pasted in the chat the 4 discussion sessions because we have 4 speakers. So perhaps I recall Xiaogang will go to discussion 1. Anton, you will go to discussion 2, if it's okay for you.